Check, 1, 2, 3. Check, 1, 2. Hello? Check, 1, 2. Check. A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P, Q, R, S, T, U, V, W, X, Y, Z. Hello? Check, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Oh, is that good? Hey, Alvaro.
If you have institutional expertise on it, that's a very different. That's a different.
What? You know I can't drink like caffeinated beverages after what happened yesterday. I am not using this mic properly. What? Yes, hello. Oh, okay. Are you familiar with using this mic? I feel like I'm hitting it. I feel like I move and it bumps into my face and makes a lot of noise. I mean, all right, I'll try not to mess up this arrangement.
Nah, you got it. You
I think it's the hair. It's got to be the hair.
put it down to your hair? I mean, your hair over.
Oh, okay. You know, I'm okay using a handheld as well. I think this will work, right? Huh? What? No, I just don't want the mic to make noise when I like move around and it bumps into my face.
Do real fast.
I'll just not move around too much.
Yeah, I don't. Your movement, if it moves or something like that, just roll with it.
All right.
I don't think you're gonna hear it too much.
Yeah, you're fine. You're not gonna do that, right?
No.
Don't disagree with me.
I mean, on the podium it says not to move around too much anyway, so. Okay.
I'm gonna ask you a question. Don't disagree with me.
Are you going to AstroTurf this presentation with fake questions? I don't know how to juggle. These people have nothing to worry about.
I definitely need help with this because StereoKit, a library I use, is just basically how to. I import 3D model. I load 3D model in. It's only 30 megabytes though, and it should store everything in VRAM. But all of a sudden, oops! Instead of using 30 megabytes of regular RAM, it uses 160.
So be ready for questions from this one.
Should ask that at your own talk, Alvaro.
Can we have this later?
Yeah.
Sorry.
Oh, keynotes.
Oh, you ready? You ready? Keynote ready?
No.
You got this. Nope. Not for that.
Anita John.
Right on time, so. Okay. Guess it's about that time, so we should get started. Oh, these levels are high on this one. Welcome to another great day at SCaLE. Hope you guys are enjoying yourselves so far. Well, this is the first talk of the first of Saturday. But before we get started, gotta say a little word from our sponsor, who's sponsoring this room. We want to say thank you to our sponsor, BuildKite, for supporting the systems and infrastructure track. BuildKite is a CI/CD platform that enables teams to build and deliver software at scale. Not this scale, but you get it. And so I'd like to introduce our speaker, Anita Zhang. And she's about to kill it. We are happy for her. Give her a big hand. Make her feel welcome. Nita, take it away.
All right, thanks. Hello, everyone. My name's Anita Zhang. I'm a software engineering manager at Meta. I support the Linux user space team, which covers systemd and basically anything in the Linux ecosystem at this point. Yeah, I know, dangerous. And today I'm going to be talking about how I debugged a memory regression in systemd journald. This is something we found when upgrading our fleet from 247 to 248. I am also an active committer to systemd, so if you'd like to ask questions about systemd after this talk, because this talk is not about systemd, that's the one at 6 o'clock. Feel free to do so. Okay, here's a rough agenda of what I'm going to be talking about. I'm going to set the stage, talk about how we discovered the issue. Then I'm going to go into how I investigated and tried to track down the root cause. Because the root cause was pretty unintuitive, I'm going to spend some time explaining in detail what happened, and then close it off with some hindsight thoughts and takeaways. So setting the stage. This is what our production fleet looked like at the time when we ran into the issue. So our entire production fleet runs CentOS Stream 8. I was also able to reproduce this issue on Fedora 34. So this occurred while upgrading systemd from 247 to 248. So this was quite a few versions ago because the latest version is now 251 upstream. Our systemd build comes from the CentOS Hyperscale SIG. My teammate Davide will be talking about Hyperscale SIG tomorrow, so you can go listen to that if you want to hear more about how we build packages for hyperscalers. But the idea behind this build is that we base it off the Fedora Rawhide spec. In this case, it was for systemd 248.2. I also mentioned here that we use kernel 5.6 at the time. This is only relevant if you want to run some of the BPF tools that I'm going to talk about in this talk. So here's what we found. I got a notice one day from the fleet efficiency team that systemd journald's average memory usage had grown since May 24th from 17 megabytes to over 50 megabytes on average. This is pretty non-trivial for our production fleet because we're running millions of servers and we want to kind of eke out all of the memory utilization that we can. And so they wanted to figure out what was going on. At the time I was rolling out systemd 248, I was pretty close to the end of the rollout at this point, so about 90% of the fleet. And I thought it was pretty strange that I didn't see this issue earlier and that this didn't actually line up with the rollout that I was doing. The way this rollout worked is that I actually had to roll back a few times, so I would have expected to see like up and down spikes in the memory usage if this was correlated with the rollout. But in this case, I didn't actually see that, so what was going on? Trust but verify, the graphs don't lie probably. So I hopped on one of the hosts. I hopped on one of the hosts that was exhibiting the issue, and I ran pmap to look at the memory mapping for systemd journald. And what I noticed that is the anonymous memory was over 300 megabytes for systemd journald, which is pretty crazy, because normally it's like 20 megabytes. Anonymous memory is important here because this is memory that's not backed by a file system. This is memory that's actually being used in the stack and heap, so it's actually in the RAM. So I was like, well, was it actually the rollout? In this graph here, it shows some of the anonymous memory growth in systemd journald. The axes are pretty small, but it was a very slow growth, about 100 kilobytes per hour. So we were like, well, if this memory growth is not showing up in 247, then it must be something in 248. But why didn't we see this as part of the rollout? Because normally when we upgrade systemd, it's a live upgrade, and the daemons will restart into the new daemons as part of the upgrade. But we noticed that for systemd journald, this wasn't actually happening. And so, since the upgrade from 248 and up, this is actually fixed, and you can actually reboot into systemd journald, which should be running the correct daemon. So for 247, we just kind of manually upgraded the systemd journald daemons, restarted them into the correct version, and that's when we were able to confirm that indeed it was the rollout, and there was something in 248 that was happening. Okay, now that we know that the issue was the rollout, we have to figure out what changed. The first thing I do, because I'm actually very in tune with what's going on in systemd, so I just go straight to the Git logs and look at what's changed in the journal. So there weren't actually that many changes in the journal code itself between 247 and 248, so I had about 5 commits to look through. Looking at the code for each one, I didn't actually see anything in particular that struck out. Maybe some of the map cache stuff was using more memory, but nothing like obvious at this point. And so I was thinking, maybe it's a memory leak. If you have like all this growth in your application, it's usually some kind of memory leak, right? But so I ran valgrand, as people do, against journald, and you notice that pretty much everything's freed. There's like these 8,000 bytes that are still reachable, but that's actually unrelated and is kind of used in every version for the mempool cache. But for the most part, nothing, everything's freed, everything's deallocated as expected. So what's going on? I'm pretty much a generalist in this space, so I had no idea what to do when debugging a memory regression in something like systemd journald. I work in other parts of systemd, but journal was kind of a mystery at this point. So I decided to just take those few journal commits that we had from the previous 2 slides and do a new systemd build based on each of those commits and deploy them on hosts and monitor for the memory regression. So theoretically, if we wait a few days, eventually we'll see on our charts that the memory growth should be growing on the bad commit, right? While that was going on, I decided to try and figure out, can I figure this out faster? Can I use some tools to debug this issue? My favorite tool of choice is usually just to jump straight to strace. Unfortunately, strace is not very good for debugging a memory regression because a lot of the memory is allocated early on by libc when the application starts. And so the kernel, you'll see like break pretty early on in the application, but the memory isn't actually allocated and mapped to physical memory until it's faulted. So that would not show up in strace, memory allocations in the kernel if you were trying to use that. What I decided to use instead was eBPF. eBPF allows you to extend the kernel capabilities without changing kernel source or loading modules, and it's become a great feature for tracing, profile, and monitoring. And so in this case, I would be able to kind of live trace what's going on in journal, hopefully get some stack traces, and figure out what's going on there. And of course, Meta is a founding member of the eBPF Foundation, so we have a lot of maintainers and others who could help if I had issues. Like I mentioned before, I'm a generalist, so I didn't really know how to debug the where I should actually go and like what BPF features I should be using. So I did some Googling, as people do, and I found Brendan Gregg's website for debugging memory leaks and memory growth. And that's what led me to try out the BCC tool suite, which has a lot of pre-built applications for tracing and debugging memory leaks and stuff. So the first tool I tried was stack count. The idea here is that if I could count the calls to malloc, maybe I could see that journal D was doing more calls to malloc than it was before, and that could explain why we had this memory growth. And so on the right here, you can see I call stack count with -u for user stack and malloc to count the calls to malloc, and I give it the PID to systemd journal D. And what I got here was one of the counts of the stack traces which lead to malloc calls. Unfortunately, when I did this between 247 and 248, the number of allocations are pretty much the same, so that was a theory that didn't work out. I was still pretty hung up about the memory leak thing, even though Valgrind was like, no, there's no memory leaks. So BCC has a tool called Mem Leak that you can run, and what it does is it tracks the allocations and deallocations that are happening in your program. So for example, if you have something that's been malloced for a really long time and it's not been freed during the lifetime of the application, that kind of thing would show up in the stack traces that Mem Leak returns. And so on the right here, I have the top 10 allocations happening in systemd journal D. I look for things that were not being freed within 10 minutes because the way our configuration was set up, we should be rotating out the journal files quite frequently. Unfortunately, this was also a dead end because I noticed that the allocations were pretty much similar between 247 and 248. All right, so let's take a step back and look at what we know so far. A lot of stuff happens in debugging. You have a lot of theories. Some of it doesn't work out. But what we know so far is that there were pretty much no leaks. I've used like multiple tools at this point. There are no extra leaks, no extra allocations. And so, where should I go from here, right? One thing I did learn from the using those BCC tools is that the allocation path, so like from getting to the journal stack where we enter the code, it starts from a client context function, and then it ends up in an allocation function that's actually in systemd's core libraries. So for example, I listed read full virtual file, which is one of the key allocation functions that journal D ends up in when it actually calls malloc and realloc. And so using this information, I decided to change my bisect strategy and start looking instead at the allocation functions. So we go to Git log once again. I look this time in the file IO functions because this is where the read full virtual file function lives. And so there are actually quite a few more. I omitted a lot of them, but this is just an example. I did the same thing. I did systemd builds on each of those commits, deployed them to machines in our fleet, and then just watched for the memory regression. And at this point, bisect prevails, and it takes us to the root cause commit, the funny or painful part of this commit. The funny or painful part of this commit is that it was actually the last commit right before 248 was tagged. So if I had done a whole bisect across all of the commits and started from the center, it would have taken quite a while. But I'll explain this more in detail about what the issue was, but the summary of what happened was normally if we were reading something from proc, we'd start with 4,000 bytes and then increase the buffer if we need more of it. But the function had changed to start from a 4 megabyte buffer, instead reallocate down to a smaller buffer as we read from proc, and we didn't need the larger buffer anymore. So, if you just think about it intuitively, it's that's fine, right? You take a larger buffer, you bring it down, you return that memory back to libc, so what's the issue here, right? All right, so let's get into the details of what happens. Let's pretend we have this heap here, this rectangle, and I'm going to talk about how some of the allocation patterns look like in systemd journal D247. So in 247, we have a bunch of Mem Leak calls. Journal reads a bunch of data from procfs, so things like the length of the command line and stuff. Those get allocated in the heap just to store the command line and stuff. If for some reason it's larger than the initial size of the buffer we set up, we'll call realloc and double the size of the buffer. If the buffer doesn't fit, then libc will just find a new space in the heap, and we, alloc new space. The old one gets freed. If for some reason that we need to allocate even more space because the data we're reading exceeded that buffer, we double it once again. Same thing. Keep calling realloc, and we actually double this up to 3 times. Most files will not, most reads will not take up all 32,000 bytes, but this is something that could happen in the code. And so the initial commit was trying to fix an issue where the maximum we actually want to allocate was not 32,000. We want to actually cap out at 4 megabytes. And so the commit was trying to fix this issue and also optimize it so that we wouldn't have to reallocate up 3 times, so we wouldn't have to retry 3 times. They thought we could just allocate everything at once and then just deallocate it down. So logically, it's it makes sense. We could save a few calls to realloc. We get the correct maximum that we're aiming for, and everything's good, right? So here's what happens in systemd journal D248. This is with the blame commit. We have the large 4 megabyte buffer. Most of the time, we're reading stuff from procfs. It's actually quite small. So a 4,000 page aligned realloc down, and we have a small buffer again. So that looks good, right? Let's pretend we have something like this on the heap, right? We have lots of little buffers scattered out throughout the heap because as the application's running, we allocate and we free memory, and we create all these free memory chunks in the heap. Unfortunately, when you're looking for an area in the heap to store this huge buffer, it couldn't fit between these gaps anymore. So instead, we have to go towards the end of the heap and malloc this big buffer there. And so now we have this large space being taken up at the end of the heap. And then, normally, like I said, procfs, we read data. We don't need the buffer that big, so it gets reallocated down. The problem here is that if we keep doing this multiple times, The way realloc works is that it tries not to copy and move the buffer to a more optimal location in the heap. Instead, it just keeps bringing it down from where it's already allocated. So if we do this, then it starts to create a lot of fragmentation in the heap. So if we were to free like one of the chunks in front of it, we start to create even more gaps in the heap, and they won't be able to store like the large buffer anymore, and we won't be able to optimally use the memory. I think another point I should bring up here is that even though we have all these free areas in the heap, to the kernel, like in the application, that memory is still mapped to a physical mapping. And that's why it says that the application's using all this memory. That memory that's like in between those allocated chunks is still being taken up by libc in your application. They're saving it for later uses. They're actually mapped. And so the kernel's like, your application's using 300 megabytes. You could realistically just be using 20. And so, the fix I ended up merging was to partially revert some of the initial blame commit. We go back to retrying 3 times to increase the size of the buffer, but I do also address the initial problem, which was they wanted to cap out at 4 megabytes instead of 32,000. So that's also been integrated in the fix. And as far as I know, Meta was kind of the first to detect and fix this issue. Kind of a benefit to the community that we run systemd upstream, or like systemd latest tag across all of our machines. So things that only show up at SCaLE, we're able to fix pretty quickly. Okay, closing it off with things that I learned in hindsight. So I want to know how I could have detected this issue faster, right? If I see this issue again, it should not take like weeks or like days to bisect an issue and track it down. Things that I should have noticed is that if I instead looked at the rate of change of anonymous memory between systemd journal D 247 and 248, sorry, I mislabeled that, it should say journal D. I would see that in 247, there was basically no rate of change in the anonymous memory, but in 248, I'd be able to see these spikes of like 4 megabyte allocations. So if I instead looked at this graph initially and like thought about it more clearly, I probably would have gone in the right direction sooner. Another thing I want to bring up because it's kind of cool is mtrace. So this is part of glibc. It's a function and a command line tool. You can insert it in like the start of your program, and it will track like allocations and deallocations. In my case, I think this was pretty similar to using BCC's Mem Leak. So, if you have the choice, you don't want to modify code, I would probably use Mem Leak. But I thought it was just cool to call out that there's also a tool in libc that you can do this programmatically in your code. Okay, another one that I thought was really cool that would have been super helpful for this investigation is massif. It comes as part of Valgrind and tracks kind of like the peak allocations happening in the heap for your application. On the left, you see that the peak memory allocation for systemd journal D 247 was around 100 kilobytes. But on the right for systemd journal D 248, you see that the peak is 4 megabytes. I've omitted here stack traces. So massif also shows you stack traces, and that would have been super helpful for tracking down where these allocations were happening and why this peak was happening. And I think if I knew that, I could have nailed down the blame commit a lot sooner. Okay. Because I am a software engineer by trade, I wanted to know, was there like another way I could have done this? Was there another fix that would have been equally, as optimal for the heap? So one idea was to, instead of using realloc, which tries to keep the start of the buffer where it is, what if we just free and call malloc again, just copy the data to another part of the heap. And so if you look at the graph on the right, I actually show 3 different builds of system journald. So the first one, that's like going all the way up, that's the system journald 248 with the memory regression. And then in the middle, closer to the bottom, is the fix that I actually upstreamed. This brings us back to baseline system journald 247 levels. And then at the bottom is the hypothetical fix that I'm listing here on the slide. Like, what if we instead just malloc memcopy free the buffer? It is slightly more optimal. I didn't end up going with this because it would have been pretty inefficient if we had to keep calling memcopy to copy data across the heap. You have to balance like memory optimization, also performance. And so I think it was just fine, the version that we ended up upstreaming. Okay, takeaways. Definitely invest in observability, monitoring, tracing, all that good stuff. I'm really fortunate that Meta has a lot of teams that makes this super easy. I could just throw these builds on the host, and I would automatically get these graphs. I didn't have to set up anything. Oh, useful stack traces. Oh yeah, one thing I didn't mention is that a lot of these BPF tools, they require frame pointers. So most builds that come straight from your distribution don't include packages with frame pointers. So if you want to get like the really nice stack traces that I had in the BCC tools I run, you should make sure your application has frame pointers. But otherwise, it's really hard to debug anything without stack traces. Okay, and yeah, always be learning. I love debugging stuff because it allows me to pick up new skills, learn about new tools. There are all these things in Valgrind beyond like the memory leak checkers that I didn't know about that I now do. And I can keep that in mind for if I have another issue like this in the future. And of course, I want to keep getting better at using eBPF. There's lots of workshops here. Tracing is just kind of super valuable nowadays for figuring out how to debug and trace down issues. All right, that's all for my talk. Thank you everyone for coming, and now I'll take questions. Yes, sir.
So, thanks for the great talk. It's really interesting. I love the technical story. I work in a bunch of different spaces, but one of the spaces I work in a lot is embedded stuff. And so we basically pretty much always end up writing our own allocators and our own subtool management and stuff like that. And so as a result, that we learn over time, we have to figure out what size subtool allocators we need. And so we built tools that examine the size of the allocated sections in the heap and try to decide what the common size of the objects that are allocated, and also note the gaps as the system runs. And we consider it to be really important to reduce, in embedded systems especially because their memory is really precious, to reduce the number of gaps by tuning the subtool allocations. Is there anything like that available on Linux at this scale?
So this gentleman mentioned that for embedded systems, we really want to decrease kind of the memory fragmentation and gaps. And is there anything in Linux that does this? Honestly, I'm not quite sure. When I was doing this investigation, I learned that there were actually lots of knobs that you can toggle in like glibc and malloc to change how the allocations work, like whether you want to cache more free buffers and things like that. But I'm not sure if there's like a tool specifically that could analyze gaps for you.
I think there's a Valgrind subtool for it, because part of the development for Valgrind is oriented around optimizing memory management and applications. And so I know that the KD folks have developed a number of things inside of Valgrind for doing memory efficiency checks for especially some of their applications doing a lot of very intense workloads that even on big computers, you kind of want to be a little bit memory efficient because you can't just throw memory at the problem forever. So I would expect if there's anywhere there would be something like that, it would probably be somewhere in Valgrind.
Yeah, Neil's right. You mentioned that there's probably something in Valgrind that would do this, and especially the KDE folks have been looking into like memory efficiency and things like that. So try and see if Valgrind has something. Yes, over there.
Not as much of a question as a comment. Might be worthwhile to get demo advice calls to if there's a unique expected to answer applications, first device that your future needs.
Yeah, this gentleman brings up a good point. We could also use in the future advice calls to see what memory allocations are happening. Okay, any other questions or comments? Yes?
Did you say that you rolled out the 240 to the dev fleet, so the hindsight could be roll it out onto to dev fleet and then see if there's a leak and then roll it to production?
Oh, for sure. So I didn't go into like this gentleman mentioned like we rolled out 248 to the entire fleet. Maybe we should have started in RC tier. I didn't go into the details of how the rollout phases work, but we always start in the RC tier. But kind of one of the downsides of the RC tier is that we don't run like all of our production workloads in it, and so we don't get all of the signal we need. Sometimes it could be rolling out to 50%, and that's when we start to see a lot of the signal in these things.
You
Yes.
mentioned RC tier. What is your tiering for rollouts? Can you explain the term?
RC stands for release candidate. In our case, we have just a bunch of machines that we run our initial binaries, such as the kernel, systemd, a lot of the widely distributed binaries. We run those first in our, you can think of it kind of a test tier, but some of them do run production workloads. And that's where we try and see if anything blows up immediately. Yes?
Great talk. It's always cool to see optimization talks, especially at web scale. Can you maybe give us a sense of scope or quantify what your fix did at Meta in terms of number of machines impacted, dollars saved?
I think the comms team doesn't want me to say anything about that. And also, I'm pretty far removed from like the dollar aspect of the machines. I think legally we're allowed to say millions of machines. But yeah, this is like the entire fleet. Like we roll out the latest systemd to like all millions of them, and it runs our production bare metal fleet. Yes.
More a comment, but there are alternative memory allocators that you can use in Linux that will try to, looking at one is like, I think you can use JE-malloc maybe to try to avoid memory fragmentation. Something, I work on embedded systems and we've also had this problem and we've worked with alternative memory allocators.
Yeah. Another audience member here just mentioned that we can use alternative memory allocators like JE-malloc, especially in embedded systems. That helps with memory fragmentation and stuff. Yes?
One more comment. I think you were lucky that you had only 247 versus 248 to compare, but when you're rolling out, usually roll out to like a newer Linux version, Linux kernel, and you got like tons of libraries that get involved with your application. Somebody else could be leaking. Any hints on how to kind of catch those type of things?
Yeah, actually, when I started this investigation, I was like, no way, this can't be systemd. Because upstream we run multiple CIs for like ASAN, and just if we saw a memory leak, we should be able to detect it immediately. I think for us, the Linux user space, the kernel teams, the container teams, we're pretty well in tune. We communicate pretty frequently amongst ourselves. And so if we notice an issue in one system where we kind of work together, communicate, and figure out, is it this rollout? Is this other rollout? And so that kind of helps narrow down the scope a lot, being able to communicate effectively between teams. And I think being able to have a very like generalist skill set, like the one I did in this case, I was able to pinpoint which system had the issue. I think being able to work across kind of a breadth of systems sometimes just to narrow down, like, it's not my application, it's your application. And having some of the data to back that up, that really helps.
Isn't that the slow loading here helped us, right? Because we could basically see the rollout and the graph change at the same time. Because we upgrade systemd independently of the rest of the distro.
Oh, yeah.
But this case was different because you needed to upgrade and restart.
Yeah.
Yeah.
Yeah, I got that compounding factor there.
Oh, yeah.
But technically you only upgrade one thing.
That's a good point. I didn't address the issue where you mentioned we could be upgrading like tons of packages at once, like when we jump between distribution versions and we have a lot of package upgrades happening. Especially, for systemd it's a lot easier because we do try to stick very closely with upstream, and the fewer divergences you have between versions, the quicker you're able to detect the issue, which is why I like running the latest systemd. It's such a big space that it covers. I want to be able to detect issues faster. Like, I wouldn't want to be running 239 and then trying to debug an issue that we now see when upgrading to 251. But for like the big distribution upgrades, for sure, we do those a lot slower. We kind of detect issues as we roll out a lot more slowly across the fleet, but it's kind of the same thing. We just keep communicating between teams. We do a lot of communications with upstream to resolve issues as well, and things like that.
Yeah, for major distribution version upgrades, a lot of the time, the teams that own major services will do their own qualification and try and figure out if there's any perfect versions before we do mass rollouts. Because that doesn't always work, but most of the time it catches at least the major issues ahead of time.
And that's why we, because we don't have a lot of resources to find and debug and fix problems, we stay much, much lower versions and let you guys figure out the problem. And then
I mean, I'm happy to do it, as long as the Linux user space team is still here.
The flip side of it, though, is that the further back you are, the harder it is actually going to get people to help you.
Yeah.
And it's even hard to integrate everything.
Right.
Like once if you move, sometimes the upgrade from a much older version is much harder. And it's really painful, especially I have felt that in embedded systems because
Same.
when I was using Yocto, like you go from one Yocto version to another Yocto version, the versions are so compatible with each other that you have a hard time upgrading the rest of the stuff.
Yeah, it's a trade-off in the end. If you're running an older stable in quotes version, it might be more stable in some end, but if you do find issues, you can't really get those upstream easily, so you have to end up maintaining a lot more test sets in-house, and that can be painful for sure.
Yeah, I at my workplace, we have personal experience dealing with this, where we run a very popular Debian-based distribution everywhere, and we've gotten to a point where we maintain somewhere between 8 to 12% backport overrides because of the main package set, because the vendor himself can't do anything to fix it. There's not a whole lot that they're willing to commit to, and nobody else wants to really work on it because it's so far behind. So working on long-term stale distributions tends to have its own set of challenges. So if you're going to go down that road, think carefully.
Okay. Does anyone else have questions about this talk or systemd in general? Okay. Well, thank you everyone for coming.
I'll take a picture of you. Can you see the bottle down? It was the whole meeting.
You should have drank
I
water.
had an egg because we had a bread emergency, but what I saw was
Hello. Oh, this works.
Hello. Hi. Well, it's very loud for a very small room, so I'll try not to be too loud. It's very hard for me. I mostly want to be very loud. So hi, I'm Michelle. My pronouns are she, her, and I work at Netflix. I'm a senior software engineer. See if this, excellent. So today I'm really excited to talk to you about Netflix workstations. Throughout this presentation, you'll see some before and after shots of work that was actually done on the workstations. You'll see some close-up beauty shots, some de-aging for some of our older celebrities, and some large environmental destruction, so things like explosions and dust, some really cool VFX work that got done. I'll be happy to answer any questions at the end as time permits, or if you find me, throughout the day in the hallway, feel free to stop me. And if nothing else, you can find me on LinkedIn. But definitely put something in the message, otherwise I'm gonna think you're a robot and not respond. Because I'm like, you're tricking me. So one question I will answer right now is that I have no power to renew or greenlight your favorite show. If I did, there would be a show called Cake with Michelle, my #1 favorite show, where I just eat cake and tell you how great it is. It'd be such a good show. It would be really boring for everyone else, but it'd be really great for me. But what I can do is help artists and creators make the Netflix originals we all know and love. My team, Production Infrastructure Engineering, or PI, is responsible for helping to make sure they can work every day, all day, and not worry about the infrastructure powering their workstations. So here's our agenda for today. We're gonna learn about what technology we used, what was the problem that we solved, who are the users, how did we actually make Netflix workstations, what did we learn, and what comes next in the Netflix Workstations 2.0. So before I talk about the problem and why we did this, I wanted to give a quick teaser trailer of the technology that we used. If you are unfamiliar with any of them, don't worry. I'll be kind of defining all these services as I go. And if you're like a super expert on any of these, please stick around and answer my questions. It'd be really helpful for my next sprint. So at the top is Go, having a cup of Java, Salt for configuration, and Spinnaker for our fleet management. Images are made with Packer, and we use a lot of AWS services. But I wanted to highlight EC2 as the actual instances, DynamoDB for the data, and SQS to support our event-driven microservices architecture. Those EC2 instances come with nice DCV, which is one of the ways we actually remote in and display it to the user, and the other one being Teradici. And since we're all about open source here, I wanted to point out some of the open source software here, which is Packer and Salt and Spinnaker, which are all really great, and if you have any questions about them specifically that you don't learn today, happy to answer how to get started with them. So what was the problem? Historically, artists had machines built for them at their desks and only had access to the data and applications when they were in the office. This system allowed for fully on-prem solutions that stopped at the door. There are a few reasons why that's not feasible. Some of them you may be well aware of, is the vast shift to work from home in 2020. We actually already started the project in late 2019 as if we were psychics, but it really accelerated our timeline to get people working as fast as possible. While people are beginning to come back to the office in some regions, the work landscape has irrevocably changed, obviously. So the second reason, and our initial project mandate, why we started in 2019, is that Netflix wants to make content at an unprecedented rate. I've worked in entertainment almost my entire career, which is about 12 years now, and I've never worked on this many entertainment projects at the same time. So we need that technology to work at this scale and be able to do it more efficiently. There are simply not enough artists in a single geographic location to support the Netflix scale of content. So productions need to meet artists where they are instead of trying to bring everyone to one giant imaginary office. And finally, by taking down traditional geographic barriers to entry, instead of making everyone move to LA, as wonderful and much as we love it here, the industry and Netflix becomes more accessible to all types of people. losing access to great talent because I live 100 miles away from the nearest office or might have mobility restrictions or other things that they want to work from home. It's just not something we want to do. Okay. So why not ship a computer is the question I'm always asked, the first question. The North Star for Netflix workstations was to provide the infrastructure for artists to get a one-click experience to go from sitting down to working on a shot. But that can also be accomplished, again, by building a computer and literally just sending it to them. So why not do that instead? There are two answers. There are flexibility and security, among many others. So production needs change fast and furious. New cameras and new software make it an ever-evolving space. By creating cloud-based workstations, adding anything from new features to security patches can be done quickly. A user can switch from one operating system to another by opening a new window instead of a new computer. Instead of waiting for a package in the mail, they can get a more powerful GPU or larger storage with a configuration change. We've had requests like this all the time, like, oh, I've run out of storage, give me some more. I'm like, okay, I'll attach some more to your new workstation, go to town, instead of waiting for something to come in the mail. Workstations, like many cloud-based applications, are not designed to be permanent. Instead, artists are renting a workstation instead of buying it. The downside to flexibility, of course, is accounting for other features that come with a single desktop. So things like persistent user settings. When working on a desktop, user and software settings are just sitting on the hard drive wherever the software puts them. With cloud-based solutions, we had to be more methodical and save crucial settings to persistent storage, associate that with a user, and attach that storage to all future workstations. So you have to be a little more, think through what are the downsides when you do something that's more flexible. For security, asset security is critical. Inside studios, files have traditionally been passed around many different ways, from FTP to email to literally someone getting on a plane with a hard drive and flying it across the ocean. So every time a file gets moved, it creates an access point for interception. By having all the assets on cloud storage along with the remote workstation, files do not have to pass through any intermediate service. No one is downloading those files to their home computer. It's all in the cloud. It also allows for this granular control of a file's lifecycle and access, so you can grant it for the short time they're working on it and then take it back, instead of being like, please delete this from your computer, pretty please. And they never have to leave the original storage. So when designing Netflix workstations, we had to balance the needs of three significant personas: artists, technical directors, and pipeline engineers. And you might not have heard those titles before, so I'm gonna kind of go into detail what they are. They're very specific animation, VFX, job titles. So, and then there's also the many supporting teams, such as storage and networking and security, all the people that make these go. So let's dig a little deeper into these personas. Artists want to focus on their art and not on technology. They are the main end users of a workstation. They want to get to work immediately and not wait for something to boot up or to figure out what files they need to download or anything. They just want to do their job. The artist workflows can vary wildly depending on the step of the production process they're on, but their basic needs are the same. You want to think of, building a movie is like moving a factory, one item from one team to another. So it's moving the shots of the film from one team to another, and they're all adding things to it to get to that final image that we all enjoy. So they have source files that include anything from, say, like original film plates that they just recorded, like a celebrity jumping away from an imaginary explosion, to reference images, to something much more technical like a LiDAR scan, to get a good idea of the 3D environment that it was filmed in. The artists then use digital content creation, or DCC apps, to create new images. That could be final drawings or the blueprint for a render. These new files then have to be shared for review. So all these steps would ideally be completed directly on the Netflix workstation, which includes other tools and plugins to manage that whole pipeline from every team to the next team, such as task management and getting reviews and things getting approved and final delivery and all the many, many steps in the movie-making factory. So technical directors are both artistic and technical expertise. Instead of working directly on shots, they work daily to improve the artist experience. They want to get the artist working faster and easier and not worrying about these things. So they need to be able to create scripts and plugins for the artists and also debug their problems. So they need to do half an artist job and half a developer's job and troubleshoot any issues. So they need a lot of observability tools, a lot of access, things like that. They decide on the software and ensure the artist on the correct configuration for their task. Things like, oh, this is the version of this software we're using for this project because this plugin works here and this will be really great for this. That sort of thing, really in the details for everything. So pipeline engineers focus exclusively on creating pipelines or workflows. So they handle that whole flow. Their portfolio can include things like file orchestration or license management or anything else needed for the artist to complete their work. They glue the pieces of the pipeline together with Netflix workstations kind of in the middle. They make sure the artist can work as efficiently and smoothly as possible, and also that the technical directors have everything they need to actually develop on workstations as well, not just make the cool images. So my team started with a strong emphasis on building a complete white glove product for the artist to use. We thought we'd build one thing and everyone would just use it and it would be great. That's never true. I don't know why we thought that. The plan was always to move towards a more self-service model, which is good because we got things in their hands and we got to see how they actually worked and get that iteration going. And I'll talk a lot more about iteration as we go on. So the first step was adding features to allow the technical directors to start to customize the experience. And the next step is moving towards a platform so the pipeline engineers control and manage their own fleets, right? They're managing everything about it, and we just make the tools available to them. So they can provide a very curated artist experience for all the teams and really customize what they see. So how do we make them? Now we're gonna start to get into technology. Starting a brand new project can involve making hundreds of decisions, both big and small. It can be very overwhelming, wondering if a choice made now will ruin an engineer's day a year from now. Well, I'm here to tell you not to worry too much about that because it definitely will. Don't worry about it, it's 100% gonna happen. So, have you ever worked on a legacy project and thought, wow, the engineer that wrote this was a genius, and everything makes sense, and it's totally perfect, and there's no weird problems with this? That's like every project, right? So, of course not. And the best part about this project is I got to be the person you're mad at, because I got to start with an MP repo and build something, and now everyone gets to be mad at me 2 years later. It's fantastic. So, as the engineer that built in the in that greenfield place, I'm the worst, but it's because I worked within the constraints of what I knew then, not what we know now, and how people would actually use what we built. So, our techniques we did use to reduce the bad choices that future engineers had to live with. For all of my technical talks, actually, I like to include this underlying theme of do less but accomplish more. That is, focus on solving the problems and only build what you absolutely have to. If there's a service or an open source tool or something's already built to solve part of your problem, just use it. And there's obviously things you need to do to vet it, but it's important that you focus on the business problems and not reinventing the wheel, right? So you can actually get things done. So Netflix actually values a culture of freedom and responsibility. You'll see that in our culture deck. And yet, a commonly used design philosophy that the engineers use is that of the paved path. It's tools and practices that are widely adopted in the company and supported. Engineers can choose any tool or build any service as part of that freedom, but then you have that responsibility to support it and maintain it. And it'll be much easier if there's already 200 people already using it and have already figured out all the problems and you can just slack them. It's the best. That kind of matched my philosophy as well and guided most of the team's choices. Of course, sometimes you can't. Sometimes you're making new things. Sometimes you're Googling something and there's literally no answers anywhere because no one has tried to do this yet. And you're like, how is this possible? I have to write a new thing? The worst. But that's when I put a premium on what tools can I use to build this, and if there's solid community adoption, as well as if I build something, can I use it in multiple problems, or am I just solving one problem? And if I'm just solving one problem, what's the smallest amount of work I can do to solve this problem? And if it's multiple problems, what do I need to do to make this flexible? It's okay. We're casual here. No problem. Okay. Tell them not to call again. You're very busy. It's very interesting. Unless you want to like put them on the phone so they can listen, because it's so good. I mean, I would recommend it. You call all your friends and be like, you have to hear this talk. The slides, there's not much on them. You won't miss it. It's just like cool pictures that I downloaded from Netflix originals, because I was like, these are the TV shows I like. Okay. So this one actually has a lot of text on it, which makes it even funnier that I made those jokes. And I'm like, oh, there's no text. It's fine, except this one has like 10 lines. So in order to explain the technology behind this project, I kind of wanted to break it down into main components. So the first component is fleet management, which is making sure the workstations are available and tracking their life cycle. Has someone acquired this workstation? Is this workstation still building? Has this workstation, is it a zombie now, which I think is the great name for something that we've lost contact with. It's obviously gone rogue and eaten all the other workstations. The second component is configuration management, which makes sure the workstations can be designed for any artist's needs, whether it's installing an application or configuring the registry or an environment variable. You can do pretty much anything to configure a computer, and we managed to find all the edge cases to do that. I've learned a lot more about PowerShell than I ever wanted to know. The following two, package and image management, are both a subset of configuration management, but they're slightly different. Package management handles those individual packages, like a single software installation, while image management handles collections of packages, such as specifying, okay, these 10 packages are required for a compositing artist. You would think installing a single piece of software is not complicated. Well, it's surprisingly complicated. A lot of things aren't as built for this type of cloud-based environment as you'd think, so you have to be, very deliberate in how you install things. So to kind of together, both the package and the image, they ensure configurations are immutable, and you need a clear history for stability and observability, like who installed this software, what was installed exactly, what was the actual lines of code they used, because that's the only way to dig into why this didn't install correctly and why it's not starting up. So the fifth component is user access, or role-based access control, and is how the right user gets the right workstation with the right files, so we're not back into that world where people have access to the wrong images and the wrong movies. And then finally, remote display protocols is how the user connects to and actually interacts with the workstation remotely. So let's start with fleet management. So fleet management handles the life cycle of a given workstation, as well as the pools of workstations with identical configurations. Pools are kind of similar to an auto-scaling group in AWS, but the control plane controls the scaling so that we're not, auto-scaling or removing things that people are currently in the middle of working on. We need a lot more information instead of letting it automatically scale. And we do that with the control plane, and that's a collection of Java Spring Boot services. Spring Boot is great. It allows for the easier creation of Java applications by abstracting away some of the common tasks. Coming from Python to Java is really nice having Spring, because I didn't have to learn something. I could just get it to work. And it has a really strong paved path in Netflix, and so many services use it. There's many people I can ask questions to. So that control plane tracks the fleet needs and alerts Spinnaker to execute them. Spinnaker describes itself as an open source, multi-cloud continuous delivery platform that helps you release software changes with high velocity. So it's a common tool for releasing and maintaining services at Netflix, and it's on the paved path. So we actually reuse this to control the workstation fleets as well. So most people are using it, I'm going to deploy my service, I'm going to make sure, do this red-black deploy, get things working. We also said, hey, we can use the same tool to deploy instances that have different configurations with these different images and control what's happening there. So it's great that we can reuse this tool. Spinnaker has this concept called pipelines, which you've already heard me use pipelines in another way, so this will be fun. I'll probably use it 5 more ways. Definitely a nice overloaded word. But in this case, they're instructions for creating the pools of workstations, which it calls clusters. So pipelines can be accessed through an API and allows for variables and expressions. So we set up a variety of variables that can be mix and match for each use case. For example, an artist can need a GPU when doing graphic-intensive work or extra large storage to handle file management. Some artists need one workstation to support the compositing software, while others require a different one to do different software. To minimize latency and get the workstations as close to the artist as possible, we also support being able to select a growing list in regions and availability zones. So we try to use the same pipeline to do everything, but here's all the variables. Launch it here, launch it there, launch it with this, that sort of thing. And that control plane directs Spinnaker pipeline to run whenever it needs either a whole pool of them, I need 100 more with a total new configuration, or I just need like 5 more workstations because I have a couple more artists coming. And it connects to the API to terminate once a user is done with it, or remove whole pools if they're like, we're done with this configuration, we're going to do a whole new one, get rid of those. And then the workstation has a Golang agent, which provides the heartbeat and other information about a workstation back to the control plane. The agent lets the control plane know when the workstation is still up and in correct state, or if it needs attention. We chose Golang here because it was easy to build for different operating systems, which we knew was an early requirement. We were going to go all over the place. Let's make sure that we can put our agent on every single type of workstation. So configuration management starts at the control plane, but the details of software installation and configuration is handled by SCaLE. We needed a system that can manage hundreds of thousands of workstations while being highly flexible and easy for anyone to jump in and create a new configuration. So not just us as the engineers, but the technical directors and everyone. We want them to think, hey, I have a new software package. How do I install it? What's an easy installation language? And that's where we chose SCaLE because it's all YAML and Jinja based, so it's a little easier to read than writing straight code. It also uses Python, which is a very common language for people in VFX and animations. They're also really familiar with that. There's a bunch of built-in modules from installing a package to file management. Copy this file over here. It also allows for logic statements to handle situations as mount this storage only in this region, or only run this script if this file doesn't exist. Please don't reinstall this software 5 times, even if this accidentally runs 5 times. And it can get complex, but at the base, it looks like this, where it's just saying, hey, install this package. And this is the equivalent here of just saying like a yum install lighting 10.1 on a CentOS instance, or apt-get install lighting 10.1 on Ubuntu. The module is OS agnostic and should find the right installer per OS. Today, there are hundreds of different packages written for the workstation, from installing the software, editing the registry, editing the environment variables, lots of different things. It was selected over other configuration management tools such as Ansible or Terraform, a question I get often, because it was used recently in our Netflix projects and got high marks, as well as being Python-based. So this is an opportunity to create bridges to the other engineers we knew would be working on this, because we knew they'd be familiar with Python. So initially, we used sort formulas directly, salt formulas, allowing for fast changes and quick deployment. Everything was always the latest, and no ability to lock to a specific version, which sounds really great, right? That seems like something that would not cause any problems, that anyone could just push some code and everyone get a different version depending on when they loaded the code. That seems right. It was a Wild West, but it was part of being able to move quickly. So to help manage that, we created a package management system that kind of wraps around those alt formulas to enforce some rules. The first is a template for all the formulas to make it easier to avoid naming conflicts and enforcing rules, such as like making sure the user information is available before this runs, or this formula is a PowerShell script, so don't run it on Linux, it won't do anything. And the second is that all the packages are immutable. To use a package on a workstation, it needs to be published to a version. If any changes are made, it needs a new version. This makes it very clear what was run. It also allows for checks at the publishing stage, such as syntax and testing. This should sound very familiar. We basically just did Git. Like we wanted to make sure there was some version control in our packaging. The structure made it easier for more of the technical directors and other engineers to contribute to the library of formulas and know exactly what code was run on the artist's workstation while not impeding their progress. They don't have to come talk to me every time they want to publish something. They just have to publish it so there's a version number so we can track down what they did. So let's talk more about image management. The image management process has gone through multiple iterations as we learned more about the users and observed how they actually use the project. And this section I kind of use as the case study of like how you iterate through a project and make it better and better as you learn more about how people use things and when the project gets better. So a workstation goes through 3 configuration stages. We have the bake, the run, and the acquire. The different iterations will show how we move the logic around to better serve the user needs once we knew how they wanted to use it. So I added the actual logic of each phase to the chart, and we'll be moving through the iterations. All of the deployed workstations start with an AMI. And AMI is an image used to launch a workstation in AWS. The bake stage is the process of turning a series of instructions into an immutable image. If you're familiar with Docker, it's just like that. Here's the script, turn it into an image, so every time I launch this instance, it's the exact same instance. So it then can be used to come up very quickly. It takes a minute or two for an EC2 instance to come up once you have that AMI. However, we found the process of baking can take a long time. We wanted to ensure that when we're in early stages, we could quickly release new features. We didn't have to wait 90 minutes every time we tried to iterate through a bug. We don't want to be held up by those long waits while it rebaked. So we only included minimal logic in the bake stage. That includes just the operating system as well as some, critical tools such as that Go agent, like, hey, this is all we need to get this workstation up. Spinnaker then creates the workstation during the run stage. Once the workstation up, that agent starts running, as well as lets the control plane know it's available, there's a new workstation. During this first iteration, there was no other configuration happening at this stage. The acquire stage is when a user asks for a workstation, like I want to get to work now. Most of the software installation, including those DCC apps, and all the user configuration happened during the acquire stage. It was kind of a just-in-time approach. Like, it's funny, I just went and got a sandwich at Jersey Mike's, and now I get to use a sandwich metaphor, which is I refused to go if we weren't going to order in advance, which is crazy because I'd let these people have their workstations and they had to wait 30 minutes. There was no ordering in advance for them. So I wouldn't accept it for sandwiches. They shouldn't accept it for the workstations. So we iterated. The long wait times led to us moving the software configuration and installation to the run stage. So this created a pool of workstations that had specific configurations and just the basic OS. However, there were 2 risks to this method. But one great thing, which is that the workstation wasn't available to acquire until everything was already installed. So when they went to acquire, it'd be fast because they didn't know it was even being made. The first risk was making of many, many pools with slight variations. That turned out not to be an issue because in practice, the usage patterns of the artists were not as diverse as initially thought. The same team tended to use the same configuration for extended periods. That meant then there were many pools. The number did not grow to be unmanageable. And the teams tended to actually just switch instead of using multiple configurations. So they'd be like, oh, we're all using this configuration. Next week, we're using this configuration. Let's get rid of the original one. The second risk was inefficiency. There were always idle workstations ready to go for artists, which meant they were sitting around just like lonely and unused and wasting compute and racking up that AWS bill, which we all love so much. That was an intentional design decision in favor of usability over efficiency. Of course, that means it's time for a third iteration. The third and current, but probably not the last iteration, is pushing the software installation to the bake stage. This is like having a library of blueprints instead of a bunch of empty houses. Real estate is not wasted because unlike houses, workstations can be built from baked images very quickly as they are needed. But don't forget, this is what we tried initially, and because of long bake times, we didn't like it. But the process has now come full circle. Instead of abandoning baking, we improved the process and developed better tooling that allows for concurrent and easier bakes and a layering system so you're not always doing a 90-minute bake, you're just adding on one piece of new software, right? And you only do a full rebake when there's something that you really need to clean up, or you need a new operating system or something that's critical. So we also kept the other option as a backup because one of the many lessons from bringing up a new project is kind of hedge your bets. You know, let the old one slowly go away while you choose the new features and see how it goes, and maybe you need to go back the old features if you haven't done the new features correctly. Real slow roll. The technical directors who handle the configuration choices are encouraged to give some time between creating a new one and letting an artist get a workstation. So that's also an improvement in like the education process. Like you shouldn't expect things right away. Like it's always gonna take some time to install. So once you make your choices, let things happen, and then you'll get your workstations. As kind of with all projects, there are no perfect choices, just a bunch of trade-offs to maximize the user experience, cost, and technical efficiency. So what we try to do here, and we'll see if maybe the next time I give this talk, the new version, there'll be iteration 4, 5, and 6. So a crucial part of any remote workstation experience is connecting to it. We currently use 2 different remote display protocols, Nice DCV and Teradici. When deciding on which remote display protocol to use, user must know how they want to connect. This is not decided by the artist, but rather by which workflow they're using. So generally, the pipeline engineers who get the artist team up and running kind of decide on the workflow based on what they need. Teradici is a commercial solution consisting of an agent, software, hardware client, and gateway components. Nice DCV is an AWS service provided by any EC2 instance and allows for a browser-based connection and application streaming. Application streaming allows for a very streamlined experience. How many times can I say streaming, but also work in Netflix? Explain so artists can jump right into their tasks without launching an entire desktop. It'd just be one piece of software. So imagine you just wanted to go into Slack, that browser would just have Slack in it. You'd get another workstation for another application, and it would just be that. While with Teradici, it's like, here's a window, it has an entire desktop on it, and your computer doesn't really have to do anything. So for both of these, the latency and peripheral connectivity were vital features. For example, if an artist can't use their Wacom tablet or their 2 giant monitors, they won't be able to do their work as well on a remote workstation. VFX and animation is very graphic and detail-oriented work. You can't have any latency. You can't have color disparities. You need to be able to see things accurately. Or otherwise, we'll get like a blue hole glitch on things, but like only in one shot. So initially, all the users acquired and accessed Netflix workstations through a UI. Key components needed to allow for improved self-service are in the UI. This includes giving the TDs the ability to create configuration and control access to them with that role-based access control, or RBAC. The UI is also for operators to visually check the health and usage of workstations, such as checking logs when a support request comes in, or making sure an artist is on the correct configuration when they say, hey, this isn't working correctly. There are also like the bigger dashboards to check on your fleets. So there's common questions like, are we out of licenses? Do we need to buy more license for this software? Or did the autoscaler go haywire and we actually requested 1,000 workstations with only Steam installed for some reason instead of any artist software? You know, that may have happened, here and there. But, we got rid of them before anyone noticed. Over the past year, we realized that stakeholders were less interested in an opinionated product and more interested in a robust and customizable platform. We're continuing to add abilities to control and customize the artist experience while improving the platform, such as reliability, observability, flexibility, all those big production level things, now that we're kind of out of that alpha stage. By focusing on these and our strong partnerships, the Netflix workstations can be leveraged for an even greater impact. So it's kind of like getting more open source contributors instead of having to do it all yourself. You just say, here's the platform, build what you'd like on top of it. So I'm just going to put it all together. The workstation starts with baking the AMI. This is where the majority of the configuration happens. Then Spinnaker handles the fleet management by turning the AMI into a workstation during the run stage. After that, the agent starts up and makes the workstation available for acquisition. Finally, once a user requests a workstation, they connect to it via the remote display protocol. When they're all done with it, the workstation gets terminated and the cycle starts again. The system is designed for artists and everyone who supports them. Artists can be onboarded no matter their geographic location to accommodate any dynamic production schedules. They can get any workstations they need with a configuration change instead of having to wait for a new one to arrive in the mail. And technical directors can quickly modify control configurations to maintain stability while pushing out new tools. Yeah, I just had recent things. Just go in, oh, this file is missing, this is wrong. Let me remote in real quick and get that for you, and now you're ready to go. And you don't have to worry about me sitting next to you. And those pipeline engineers can build on top of the platform to customize the experience to a specific artist workflow and have whatever you're doing, whether it's 1 frame, 1,000 frames, this software, that software, you can have the system ready for you. So here's what it looks like today for a user to request a workstation. It goes by like really fast, but it repeats so you can see it happening over and over again. They select the workstation and the configuration they need. They wait a very reasonable amount of time for the workstation to prep. Then they select the connection. In this case, it's nice ECV, so they'll be opening it in the browser. And then there it is, a desktop with a few tools already open automatically. So that's another thing you can configure, like, hey, when this loads up, automatically open these tools because these are the ones they're going to use. And if you can catch it, you can see Deadline, another AWS tool that we use for rendering, right at the bottom of the taskbar. I'll go one more. See, very reasonable amount of time. I didn't edit that into the GIF, that it went so fast. Definitely. So what did we learn here? You always want to debrief your projects to make them better, and that's what we did. So everything was new when the project started. These were new roles, new team, and an empty repository. We made the best choices with the information we had, then we pivoted when real-world users showed us a different way. Here's some of what we learned about designing artist-driven technology. So nothing can be taken for granted when making a significant leap in technology at your company. The new technology of cloud-based workstations must, at the very least, match the old experience of dedicated on-prem workstations, or the user won't use it. Having the exact same experience is the table stakes. The things they're used to have to be there at least. For example, they rely on their software settings to remain in place from one workday to the next. But if it's not, that's not a given on a cloud-based workstation. You have to be more methodical about it. Therefore, it's like super essential to learn everything that people are doing so nothing is missed in a user's workflow, and then improving it. Because why convince them to use a new thing if it's not better than their old thing? We've focused first on technical flexibility instead of the artist experience. But artists needed custom workflows, not standard solutions. By initially building the entire product, we kind of painted ourselves into a corner. We were on the hook for making everything, but unable to deliver the needed customizations because we had limited engineers. Instead, we're pivoting to a platform to build a strong core and allow for partner customization. Empowering others to develop with you gives your teams more leverage than they can accomplish as individuals. The more the system makes it easier for others to contribute, the better the adoption and the iteration will be. People will do things that you never expected them to do, which is great because then you don't have to do it, and they're doing it. The engineers need to help each other. It's critical to empathize with your users. When an artist calls me, I know it is the worst part of their day. That's what I've known the entire time I've worked in entertainment. They want to focus on their art and not on whatever it is you broke today because you pushed something. Observability and testing can seem like things that can be cut when timelines compress. Say, you thought you had a year to build remote workstations, and then you've only worked there 2 months, and everyone is home now. But they quickly come back and haunt you, especially when you're on call. So we committed to improving in those areas and adding more robust automated testing, clearer failure modes, reporting, all the like good stuff you want in production that you were like, oh, we don't need this right now. We just need to get this to work. But you need to get it to work. And finally, addressing one use case at a time from the micro to the macro level, addressing one operating system, making sure that works, or addressing one user persona first, and then moving on to the next theme, and really hardening as you go. From the small tickets and the small pull requests, the small releases, things we tried to abstract too early and be like, oh, this will work for all use cases, never got it right, and we ended up having to rewrite it anyway. So it's better to just, for us, to do one thing at a time, and then you see, oh, this is how all these 5 teams are using the same way, and now we can abstract things out and know you're on the right track. So what's next? Like the Christmas Prince universe, crossovers and spin-offs make things more fun. I hope you all enjoy the many Christmas Prince movies that Netflix provides. Netflix workstations are kind of one part of a technology ecosystem designed to help content creators make feature films and television at an unprecedented rate. So you have new things every week to watch, and you always stay a Netflix subscriber. It consists of many other teams that help our infrastructure in new and exciting ways. We'll be collaborating to plug workstations into more and more workflows, so more things are automated, more things are done quicker and easier, and we always know what's going on. So our talent worldwide can be part of making diverse content. So thank you for listening. It's been fun. And I want to thank my many stunning colleagues, without whom there'd be no Netflix workstations. And I think we have time for questions. I think we have about 10 minutes. So if there are any questions, let me know. Go ahead.
How do you achieve the same frames per second when you're going over net versus GPU to display?
So he asked, how do you get the same frame per second in Netflix workstation? So one of the things we do is just being local regions, like making sure that there's a workstation as close to the artist as possible. If we know someone's going to be working in this country or this city, let's get in this availability zone. The second is we're really relying on our remote display providers to get that work and get that latency down. So you see both those things, like making sure you don't feel the latency when you're close enough. Because I have to test workstations, obviously, that are all over the world, and I will notice it. I'll notice a latency if I'm working on a workstation across the world, but the artist won't because it's right next to them. And then relying on the actual graphics and getting the pixels there as fast as possible, that's our great partners at Teradici and ICCV. Luckily, I don't have to do everything. Go ahead. Yeah, so the RDPs, those two, Teradici and ICCV, they're not proprietary to Netflix. Anytime we could buy or borrow, I really like that because I don't have to build my own thing. So Teradici is commercial software. And then NiceDCV is on your EC2 instance. So when people are like, hey, I want to try out, doing a remote workstation, I always tell people, this is what I think you should try out first. This is the first workflow. You go build an EC2 instance, and then install NiceDCV and go see how it works for you because it's already there in AWS for you. And if you decide, oh, maybe I want the Teradici experience, then you'll at least know that it already works. I think there's one over there. Yeah. Yeah. So there's a lot where so he asked about color management. Obviously, color is very important to getting your film all correctly. So some of that is the back-end technology that you use in film production, right? So there's this idea of color spaces, and those are all math. So that's happening as part of the process behind the scenes when you're generating the image. You're deciding, okay, this entire film is going to use this math formula so that when they all come out at the end, all the images look matched together. So that's part of it, and that's kind of outside of Netflix workstations, but it's just how movies work, right? The other part of it is relying on our remote display protocol partners, and then also on the monitors and the environment that the user is in. So sometimes people ask me like, hey, can people work on their workstation outside? And I'm like, no, they're doing color sensitive work. Of course they're not working outside. Like that's the difference between like making a remote workstation for a developer. Of course you can work outside as long as you can see your IDE and have access to Stack Overflow, you can work outside. But there's a lot of things that go into making the color correct. And if our RDP protocols aren't right and things are off, or if their environment isn't correct, or if the color space or that math isn't correct, that could all lead to different color options. So there's a lot of people working hard making sure that that is 100% accurate. And they need really nice monitors and a nice room. When I used to work inside a VFX facility, it was actually no lights allowed. So like imagine like a normal office with like cubicles, but like everyone's just like sitting in the dark, like it's like Severance. So it's actually pretty funny. But like they have to, right? Because they can't have that glare on their monitor when making feature films. Go ahead.
What adjustments would you make due to the need for more variances in configuration or user roles?
Yeah, he asked what changes we would make if we had more variables and configuration that we need to do. I think we're already doing that now, which is letting the users control the configurations and build their own stuff. So when we first started, they'd be like, I want a workstation with this on it, and I'd literally like download the software and figure out how to install it and set up the formula and package it for them and then give it to them. Now I'm like, okay, here's our platform, here's where you put any files you need on S3, here's where you configure it in this repository, here's how you build an image, go to town, test it, try it out yourself. So by kind of outsourcing to the people who want to use it, they can make as many configurations as they want, and we're there to make the tools easier. He asked if it also increases the support workload, and it kind of depends, right? Like we're on the hook for the infrastructure, and making sure that it works and the basics work, and when they go to log in, they don't get a connection error. But if they've installed software and the software doesn't run correctly, we just bring it back to them and say, like, hey, you ran this, I see this is your code. If there's like confusion on how to use the tools, that's part of our support burden. That's part of like, oh, I noticed you tried to do this and you got an error. Did that error make sense? Do you know how to fix it? But most of the time, we try to have good messaging so people can see like, oh, I tried to install the software and it says file doesn't exist. And it says where in S3 it look for it, and the file isn't there. Maybe I should upload the file to S3 where I said it should be, Things like that, where it's like we're trying to be more of a platform and a tool system and not debug every piece of software, because there's a lot of software that takes a lot of expertise to install correctly. There's just some DC apps that are just like, you don't know how much time I spent in the first round trying to get this thing to install, and it's like wild to install correctly on the cloud versus a desktop. So. And into an image. It's very different installing on an image than it is installing on a machine that's always going to be running and you just leave it. So there's a lot of, I always call image making like the devil in the details. So having more people involved in configuring their own configurations actually helps to disperse that knowledge, because they should be experts on the software they want to use. Go ahead, back there. Yeah, so there's Teradici and NiceDCV. Those are the two. You can also just like RDP into them if you're like a power user. I use that sometimes when I'm debugging. I just use the one I really like. It's called like Royal TSV. It has a lot of options for remoting in, but that's not like for like the artist experience. The artist experience, we use the Teradici client or the NiceDCV client, because that's a really nice streamlined experience where we actually generate short-term use codes for them every time they want to log on. So we're constantly checking their credentials, because security is so important in movies. So it's like a different experience, but like as a power user, you can kind of get in any way you want. You can use Microsoft Remote Desktop to go in. I'm sorry, can you say again? We haven't tried that, no. Teradici was kind of one that's been used. Other entertainment companies have used it well before, and so we wanted to use something that people were a little familiar with, and it worked well for us. And then the nice DCV we just liked for the application streaming, and the fact that it comes free with an EC2 instance that we were already using. So if we run into other use cases where those two don't work, we might explore other options, but that's part of the it's in my general philosophy not to build new features until someone actually needs it. So people sometimes ask I'll get an error, and I'll be like, oh, were you trying to do something? Do you need a new feature? And they'll be like, no. I'm like, great. Do it the other way then. Do it the normal way. So.
Are there any other groups that are looking to leverage this stuff besides just artists?
Yeah, so we focus primarily on studio, but there's a lot of different teams at Netflix that are interested in this. But it's interesting because studio is a very specific area where they need that color accuracy. They need that a lot of storage. Movies are very big. We need to not lose anything. It's also very different than if you think about streaming, you're watching Netflix, that's 200 million users, so everything has to be very resilient, but a single user is less important than the group. But if you think about Netflix workstations, it's an internal tool for artists. And if one artist cannot work, that is an emergency. They get to call me at 3 a.m. if they can't do their work for that day, because you can't let people lose a work day. That's awful. They're not getting paid, the work isn't getting done. So it's a very different experience.
I think what I'm more interested in is if there are other businesses at Netflix games.
Yeah. Yeah, we're definitely exploring it, but we really want to make sure that we don't stretch. So we asked if Netflix Games was going to use this, and it's definitely something that is possible, but we don't want to stretch too far until we're really sure. So, as I kind of mentioned in the beginning, we stretched really far in March, April, May 2020, and now we're make sure everything works really well, and then we're going to say, okay, how do we get new users? What other groups want to jump into this? And without changing too much. So something like games is actually very similar to VFX and animation, so it might fit better than, say, for engineers who have a totally different workflow. But engineers and TDs actually don't have that different of a workflow. So it's an interesting what to focus on in any project, user expansion versus technology hardening. And you always don't want to go too far in one direction where you get too many users and suddenly nothing works, or you spend too much time on technology hardening and you've actually gone in the wrong direction because your users, if you'd expanded users, you would have gotten more information. So we're trying to balance it a little better now that we're not in a rush. But it's definitely, I want as many users as possible. Go ahead.
Are the TDs and pipeline engineers, are they able to achieve this, zero client, zero endpoint? You know what I mean by that?
Yes. He asked about zero clients, and I said yes. And that's about all I know about zero clients. So hopefully there's no follow-up questions. I've heard the phrase zero clients, and they've used them. I believe it's when you have a very thin client, right? Where it's I get into workstations on my MacBook, but that's super overkill because I already have a MacBook. But if I just had imagine a computer's just a little tiny thing instead of an entire computer that all it does is log into remote workstations. That's another use case that people actually often use, because if they had a regular computer, why would they need a remote workstation? Go ahead. Oh, sorry. Guy in the gray shirt and then the guy in the black shirt.
Is it the cloud is very expensive to run on comparing to the network hardware? Because if the user is equipped with the CPU, the EC2 can be very, very expensive.
Yes. But, okay, if you think about it, the computers that they were using at their desks were also very expensive. Artists usually don't have nice cheap computers. You can't give an artist a Chromebook. I don't know if anyone's ever seen a box desktop. It's very common. It's just they have to be so substantial anyway that using the cloud isn't making as big of a difference. So if you're exchanging your Chromebook for an EC2 instance, you'll see a much bigger leap in cost than you'll see if you're exchanging your powerhouse gaming rig for an EC2 instance. You see what I mean? There's not traveling as much in cost, But one of the initiatives, like I talked about the efficiency of not having idle instances sitting around, is to do things like that, is to like lower our unneeded costs. It's needed to have an EC2 instance that has a great graphics card and has a lot of storage. That's a needed cost. Having extra idle workstations that no one's using, that's an unneeded cost. So that's what we focus on, is making sure any extra costs we don't have, instead of the ones that are actually necessary. Okay. Yeah, definitely. So there's there's so many things. Like, we use this UI, and you saw it a little bit in the GIF, but that's just like the artist view, and like the admin view is very different. So you can see things like open a workstation and see all the graphs of things like CPU and memory and that sort of thing. So like if you see something spiking and starting to hit the limit, you'll get that alert before they do. Seeing storage before it hits the limit, so you get the alert before they do. Seeing, hey, this person logged in 5 times over 20 minutes. What's that about? Like, seeing these patterns of usage is really important to spot, like, patterns of problem. Or, even grander, like, hey, 30 people tried to log in and 30 people had failures. All right, something major is down, then seeing that. So it's about both the macro and that micro level. So we added a lot of logging and graphs and things like that to the individual workstation page in the UI, where you can see all the details about it and make it a lot easier to debug. And then we are also starting to learn those patterns by aggregating the data and seeing over time how people are using them. That answer your question? Okay. Go ahead.
I'm not sure enough about how the visual effects software works, but are there automated, this is a follow-up to the question about cost and compilation. Are there automated or batch things that are run, and can those be run? You guys ever tried to use a fleet of spot instances to manage the cost?
Yes, we call that rendering. It happens all the time. So what an artist usually makes, they don't actually usually make the final image. They actually make a blueprint. So this is all, it's like artistry and math at the same time. So they get like they'll get like a film plate, they'll get the original film, and then they'll say like, add this in here, add this in here, add this in here, but they'll be working on a very low resolution version of it. And then what rendering does is it takes that image and it takes the selections they've made and does a bunch of math and creates that like final beautiful image. So that's like the headless version. Yeah, you don't need like a whole workstation to do that. It's actually a super common VFX way of doing things. And if you look, there's like the very fast in the GIF, I featured Deadline, which is a monitoring tool that helps you monitor render. So that when you're on a workstation and you say, launch my render to somewhere else in the cloud that does the render, you can see it monitored on your workstation. So that is an extremely common process. That's how all movies get made. But it's a little different because it's completely headless. Go ahead. We allocate a pool so that they're always available. He asked about we're allocating a pool for spot instances or reserved, and it's less about pricing and more about that an artist can come in and immediately have something. Oh, we're at time. Someone was gesturing, and I didn't know what he was talking about, but it looks like we're at time. So I'm gonna stop with the questions, but so great to have all these questions. I love all the interest. Feel free to find me out, like hang out outside, or again on LinkedIn, leave a message so I know you're not a robot. Thank you.
Is it here? Can you hear it now? Oh, there you go. Hey, go. Thanks. I like the feedback, so if we can make this interactive, that'd be great. So anyway, the point is that I am not going to apologize for anything other than the slides. So some people did help me get them at the last minute to have some nice look and feel and all that kind of stuff, but the content is definitely put on there very rushed. All right, so I don't want to apologize any further. Let's just go ahead and get started. Chaos is a feature, not a bug. The point is that we don't want to have it happen to us. We want to get out in front of it, right? So some of the topics I'm going to cover here are a little bit of an intro to chaos, especially around like reliability and resilience. You got to talk about that first. Chaos engineering, of course, and fault injection. And talk a little bit about Litmus Chaos. It's the open source project that my company Harness acquired, and the team that comes with it. So we now have a really nice staff of chaos experts. The company that we acquired was called Chaos Native, and Litmus Chaos is the open source project that they submitted to the CNCF, and it's now incubating. And we'll talk a little bit about game days or chaos days. You know, game days can mean different things, right? So specifically a chaos type game day. So first, another thing, let me do this. Let me change this a little bit. I have some notes in here. It'd be helpful if I did this in presenter view. I think you still should be able to see, well now you can see what I see, right? How can I do this in a way that's a little bit more useful to you? Let's see here. Let's see, hold on, let me go back. It put me in a different view. Okay, I should probably get prepared for this before I do start my presentation. Hold on one second, let me just stop this for a second. Because I can't figure out how to do this real quick. Hold on. All right. Let me go find my slides. Okay, now let's see, if I go into presenter view, still doing that, huh? Oh, okay, thanks. Let's go, do I stop mirroring? Is that what I do? Okay, so we're back to not stop mirroring. Okay, now we go into, let's see, do I move this over? Okay. All right, and now I can go into, I just can't see what I'm doing over there. Does that do it? All right, now what happens if I go slide by slide? Oh, good, we're in good shape. All right, thanks for hanging with me on that. Okay, so these are some of the subjects we're going to cover. I already covered that slide. All right, so first, before we start talking about chaos engineering, it's important to understand the core, site reliability engineering concepts, that we're going to be applying this to. So, for example, and again, sorry for the mix-up on the slides here or the mess. For example, it's never really been easier to create large-scale applications that are distributed. We've got Kubernetes, we've got all these tools that help us do this and make bigger and grander and more scalable websites, right? And so, by example of this, we've now got our infrastructures in the cloud, we've got an amazing programming language support. There are lots and lots of open source projects and components that we can use, and we've got lots and lots of services now. And so it is easier than ever to build an incredibly large and complicated website. And so, you know, I remember I've been in this space for a while, or a long time. I've been in DevRel since the early days of APIs, and I remember in the early days, you couldn't get somebody to use your API because they would tell you, why on earth would I want to add your downtime to my downtime, right? That's how it was back then. Downtime was significant. And you know, these days, we don't think that way as much. We still do a little bit, but you know, we don't really think too hard about using somebody else's service through an API because their downtime's probably pretty reasonable, you know, especially if they're of any size. And so that's not that big of a deal. So we'll add that to our service. However, this creates a lot of opportunity for issues. And so, you know, nothing is 100% reliable. And so the larger your application, the more of these components and these services that you add, that creates more surface area of more problems that could occur. Even like you know, Amazon S3 or Google Storage or Azure Storage, you know, those have downtime too, even though it seems like they don't, right? Because how many nines do they have these days? But there are times when they've had outages. And so that's where resilience comes in, all right? So there is no guarantee that these things won't go down, and so you know, these are the services that our systems are built upon. And so any of this infrastructure can go offline at any point in time, and you need a plan. You need a plan that your applications and service will go down, and so there will be disruptions. And to deal with this, you think about those components as being, so they have some kind of reliability, right? And then if your individual component goes down, then how do you deal with that is really the resilience. So how resilient is your application when some parts of it go down? So resiliency is the ability to withstand certain types of failure in your components or the pieces, and yet remain functional to some level. And so you can't be resilient if the components that make up your system are not reliable, or have some sort of known reliability. And so this talk, we're going to talk about how you can make your deployments more reliable through chaos engineering. All right, who am I? My name is Dave Nielsen, and I work as the Senior Director of Developer Relations, or Community and Advocacy at Harness. And some of the things you should know just about Harness is that while we started off as a purely CD company, is this advancing? Yeah, okay. Doing continuous delivery, we then acquired an open source project called Drone. And Drone is like the best kept secret. It was created when Docker came out, and Brad, the creator of Drone, felt that continuous integration should be done in containers, because all of those tests and all the different steps in the pipeline, you don't want them to impact each other. Especially if any of you have used like Jenkins, those different steps along the way sometimes share code bases or the platform, the programming language, and so upgrading any of your steps along the way could be pretty difficult. But if everything's running in containers and you just want to update one of those steps, you just update the container, and it could be a different version of the programming language. It can be a different programming language altogether. And so he built that. That's what Drone became. And you choose your plugins, is what we call those, and you set it up with YAML, and you're off and running. It's very simple. But anyway, more or less a one-man show. I mean, he definitely had some others helping him, and he had a great group of volunteers building all these plugins. But almost 2 years ago, we acquired Drone, and but it had already reached hundreds of millions of downloads with this one plus person show that had never raised any funding. Pretty amazing. I used to work at Redis, and there's a similar story there with Salvatore, the creator of Redis, and it's just really amazing when these things happen. So I'm really excited to be helping to promote Drone, which is a different subject, but that is how we got our open source community going, or that's most of our open source community. And then we acquired Litmus Chaos, which has a similar story, but more recent. And so now we have 2 open source projects as a part of our community. Okay, so failures are inherent to complex systems, and so what do we mean by complex? Basically, you've got, even in like a mono repo, it can be very complex. But now that we've got all of the different systems that are, microservices, different teams, it becomes so much more complex. It's almost, exponentially more complex. And so a system would be made up of multiple components. Each component might have its own reliability, but really what we're talking about is, how does the overall system behave? Sometimes there might be a rippling effect, and you just don't know how the other components in your system might behave if one system goes down. So that's a complex system where you just don't really know how all of them will behave if one thing changes. And so there's lots of examples where there's been outages. And why have these outages occurred? Well, so for example, Salesforce.com, they're a big company, they know what they're doing, and yet, boom, they had a DNS outage. And what does it go? I forget how the quote goes, but it's something like, it's never DNS. It was DNS. There you go. Thank you. That was it. Thank you. Yeah, that's the one I was looking for. It's not DNS. Okay, it was DNS. All right. So doesn't DNS seem like one of those things that would be ridiculously reliable, and yet it's a complex system too. And that one took over a week to recover from. So clearly they had not done a chaos experiment on this problem. Otherwise, I don't think it would have taken a week to recover. Cloudflare. This one was interesting because this occurred when they ran a script, it's a bash script, but they didn't use pipe fail. And so what happens when you don't use pipe fail? If one of the commands has an error and you're expecting it to result in some data, it's just going to continue on and continue to do run the script, but there's no data. So what happens is it goes and replaces data with no data. And in this case, that caused a big problem for them because they basically passed in a 0-row array into the next step, which then replaced all of their data with nothing. So, and that was a pretty big outage. Then Atlassian had one. This is another example of where, there was miscommunication. They were supposed to delete some accounts. They passed in the wrong data. Like the one team gave the wrong data to the other team. And then on top of that, they had a script that said, delete these accounts, or mark them for deletion. But in the same script was, no, delete them permanently. And so they ran the wrong one. And so not only did they pass in the wrong account information, they then deleted them permanently. So that was a difficult one for them to recover from. So there's lots of different ones. This is one I personally experienced. I was at PayPal many years ago, and we were, some of you may have had this experience. So I remember sitting in the room when the consulting company that we had hired to tell us how to make a big change in our application, basically, PayPal was able to get to 50 million users on one database. Yeah. So we were running on an Oracle database on the biggest, baddest, Sun Solaris box that they could possibly have. And the consulting company came in and said, in about 6 months, there's nothing we can do to make this go any faster, and we're going to run out of capacity. And so the company literally stopped marketing everything because it'd be much worse for some financial type website to not be able to respond to people and their money than it would be to not have as many users. And so we literally tried to put on the brakes, but PayPal was so viral that even with zero marketing, it just continued to grow. And so we hit that 6 month mark right about the time we were doing the update, but it was that's a race condition. We were really worried about the website, the database falling apart. So anyway, all the testing was probably not done very well, and there were so many dependencies because we took what was a single database and we built APIs on top of it, but those APIs were really kind of, I don't know. All I can say is that we took processes and tried to split them out across multiple copies of the database, and once we put that into production, we didn't know what to expect, and it turned out there was rolling blackouts, essentially. So about every couple days, the website would just crash. So I think more testing and perhaps chaos would have helped there as well. So there's a lot of examples, and these examples are very expensive. This is just a quick chart. I'm not going to even tell you what the numbers are. They're big, $30 million per outage, that kind of thing. So the problem is that it's very hard to test all of the different combinations of things that you need to test. And so a lot of times what happens is that we do the things that we know to test and what we think are important, and at some point there's just not enough time. And so we may not test things. In fact, I put this up here because sometimes you just say, I don't know what the problem is, I don't know what the results would be if I don't do this, so I'm just not going to decide to do it now. But the problem is you actually are making a choice, right? You're making a choice not to do that. And so you don't know what's going to happen, but when some people say, we're not running experiments, I'm saying, yes, you are, you just don't know what they are. And so there's a lot of different things that happen out there, and I won't spend much time on this slide, but yeah, there's just a ridiculous number of things that can happen. I remember, the test that we used to do a long time ago was just simply unplugging things. That was a pretty easy and cheap one to do, which kind of works. But there's just so many things that can happen. You certainly can't just do them all yourself. All right, so what are some real-world examples of things that might happen? Well, first of all, I was doing some research in the last week on all of this, and one of the things I ran across is that, now this is over the past 25 years, so it's definitely a lot of things have changed in that period of time, but over the past 25 years, according to the research I read, 80% of all load losses were in data centers were human caused. All right, and I said this, the very first person in our SRE team that I ran across, I mentioned this to him, and he's like, oh yeah. I'm like, what? He's like, oh yeah, my first day on the job, I tripped over a cord, took out the entire data center. I was like, oh my gosh, really? He's like, yeah, but if things, we've gotten better at this kind of stuff, those cords aren't laying around as much. But anyway, there's other issues that are real world examples, like, resource exhaustion. And, I was at Redis, and one of the things that we would exhaust is memory, okay? And that would cause a problem, right? So that would be one type. Or just your database fills up the hard drive, right? Or your logs fill up the hard drive. I mean, there's all these things. Hardware failures, of course. Network latency. A sudden increase or decrease in usage, that could cause problems. I mean, increase you can understand, but even sometimes going down can cause problems. Downstream dependencies. Of course, functional bugs. Those are some of the ones I mentioned possibly. Race conditions, state transmission errors between senders, unusual combinations of inter-service communications. And I named this one, this is just me making things up here, but the Dunning-Kruger problem, when one node thinks it has all the correct information, but it doesn't. And so it thinks it's doing all the right things, but it's not. Okay, so some of these examples. How many of you have experienced possibly one of these examples? Okay, yeah. Any example that you don't see up here? Yeah. What's that? Air quotations? Air conditioning. Oh, air conditioning. Okay. Like heat? Yeah. Air conditioner. Yeah. Yes.
I took down Schwab.com once when I accidentally took everything out of load balance instead of just half the stuff out of load balance.
Right. Excellent. Yeah, air conditioning, actually my first ever job was when I was in high school. I went into a mortgage business and my job was to do the backup of the tapes. It's, you know, they had this cold room with all the tapes in it and I'd go in there and whatever. So when I graduated, I found somebody to replace me, and at one point, I remember I didn't actually know that person that well, but I knew the people at the mortgage company, and so at one point I'm like, hey, how'd that go with that guy? And he's like, yeah, not so good. Like, what happened? He's like, well, he got cold one day, so he turned off the air conditioning. And they didn't figure that out for almost 2 weeks, so they basically ended up with roughly about a week's worth of no backup. So they were lucky that nothing terrible happened. Yeah, so he didn't last long. Yeah, exactly. So, all right, now that we've talked about all that, what is chaos engineering? All right, so it's the practice of subjecting applications. I'm going to read to you here. It's the practice of subjecting applications and services to real-world stresses and failures in order to build and validate resilience to unreliable conditions and missing dependencies. Okay, so that's what it is. This was from a Microsoft website. I think later on I talk about some Azure stuff. I'm trying to, or some AWS stuff. I'm trying to, be fair to folks. And the next one is fault injection. All right, so what is fault injection? So it's the act of introducing an error to a system. Different faults such as network latency or loss or of access to storage can be used to target system components, causing scenarios that an application or service must be able to handle or recover from. So chaos engineering is more like the overall practice, and then as a part of that, you're going to run these individual experiments. Those are the fault injections. Okay, so now what about chaos engineering? Where does it come from? Was anybody around when Adrian Cockcroft was giving those early talks? Anybody? Oh, okay. Well, I happen to have been there. I work in Silicon Valley, and I run Silicon Valley DevOps, and I also ran this event called Cloud Camp. And between those two events, I gave lots and lots of people opportunity to talk. And Adrian submitted a talk to Cloud Camp. I think it was Cloud Camp. And I'd already known him from talking about other things. Of course, we accepted his talk, and he gave, I believe, one of the very first talks about Chaos Monkey at Cloud Camp. And over the years, I've had him speak on different topics, but I remember I quoted him on a couple things on Twitter, and I think I got hundreds of likes. Like, it was definitely like a moment I'm like, oh, people like this. So that was kind of cool. But it goes even further back to maybe Jesse Robbins. He was one of the ones who was actually doing similar things, like just physically unplugging hardware, to create tests, at Amazon. And then over the time, Netflix ended up not only having the Chaos Monkey, which basically did shut down instances, that's basically what it was doing, but then they would do other things, right? They would create other monkeys that had different skills, and they had the one that would shut down the whole region. That was the Chaos Gorilla, or they had ones that would, kind of make it look like the server was slowly responding, so over time, right? So it'd slow down its responsiveness. And so they had all these different monkeys, and they ended up calling that the Simeon Army. And this was a big deal in the time. It was very, very innovative, and a lot of us were like, wow, I hope I can someday, have a website that would deserve this kind of attention. But, this concept definitely grew and grew and grew, and then around 2014, they coined the term chaos engineer, and then 2020, Amazon added their reliability, which is including chaos engineering, to the AWS well-architected framework. Litmus Chaos was donated to CNCF in 2020 as well, and then now it's at the incubation level. All right, so this is very short and very biased history, but this is my history with chaos. And so folks are definitely not just talking about it anymore, and they're not, it's no longer just chapters. There's like multiple books about this. Has become a big deal. And by the way, there's some really good books in here. So, and if you haven't already checked this out, I think the AWS Well Architect Framework is a good one to go look at. Specifically, there is the reliability pillar, and there's a lot on this subject there, and some on chaos engineering. Yeah.
Were you going to make your slides available?
Yeah, I'll make them available. Yeah, you bet. How am I going to make them available? At the end, I have my contact information, so you can email me. That's probably the easiest way. Okay. So why are we seeing this now? All right. Well, so more and more and more, I think, the way I think of these things is that it just takes time for some of these higher level, more long tail concepts to come to attention. But as we solve more of the immediate problems, we are able to solve start turning our attention to the ones that may not happen today, but may happen tomorrow. And so, also, I think during COVID, I think there were a whole bunch of new websites that spun up really quick and had a lot of problems, and there were a lot of people using them. So I think maybe all of a sudden we had a new appreciation for reliability. And then finally, I think just as Kubernetes makes it possible to spin up more container images, and your application might grow and have more surface area because it's easier, it's also easier to spin up an entire copy of your application and run chaos on that, which was not something that was really possible before the cloud, or extremely expensive because you basically had to own a copy of all of the hardware, right? By the way, this is also something we discovered as a part of continuous delivery, which again, what our company does, because when we run, you can run canary deployments, you can do rollouts, but if you want to do a blue-green, you're doing an entire copy of your infrastructure. And so that's something that is relatively recent. So it's kind of a similar thing. And by the way, if you roll out an entire copy to do a blue-green deployment, isn't that a great time to run a chaos experiment? Right? You got the whole thing right there, and you haven't switched it yet to be production. Perfect time. Okay, so also I think what's happening is that as it becomes more important, there's people who've been doing this for a long time, and they're like, we now all of a sudden have our moment in the sun and in the light, and we want a name for what we're doing. And so I'm making this up today. I'm now introducing to you Dev Reliability Ops. Okay, I'm joking, but no. Just like DevSecOps, there are some people in the DevOps space who would be saying, isn't DevSecOps just DevOps, right? Shouldn't we be doing security as a part of DevOps? Like, does there have to be a whole separate thing? And I think it's the same thing with chaos. I think there shouldn't be Dev Reliability Ops. It just should be part of DevOps. Maybe we'll spend more time on it than we used to, but that's the way I look at it. Also, I think it's important now for, I think from what I've seen and read is that chaos is actually a very good team building exercise to run those kind of experiments because they do require working together and understanding each other, creating compassion for like some of the people who have to deal with some really big issues, whereas others may not. So I think it's great for internal teamwork, not just for customers. All right, so here I just want to mention, Litmus Chaos is also, we're starting to see more open source projects. One of them is Litmus Chaos, and it's a great tool for running your experiments. So I'll talk a little bit more about it, but this project started actually from the team that created Chaos Native actually was the same team, or mostly the same team from OpenEBS, and they had done some experiments to kind of do chaos. They had basically built one or two experiments on their own for their own product to test it, and that eventually became what is Chaos Native, and so that's where it came from. And also, one thing that's interesting is like one of the things that's interesting about Chaos Native is that, or Litmus Chaos, is that it's very declarative in the way that you describe what you want to occur, and that's become popular. It's becoming more and more popular. So I think folks kind of gravitated, folks who were interested in more declarative type of pipeline creation were attracted to this. Okay, and you can learn more about Limitless Chaos. It is a CNCF incubating project, and there's lots of users, and it's growing on, so on and so forth. The project's growing. A couple things I'll just point out, which I can't really see here, but I'll try to get close. Well, there you go. So scheduling all of these experiments is actually really difficult, especially if you're trying to decide in which order your experiments go and all that kind of stuff. So that's one of the main things that you'll get from an open source project like Limitless Chaos, is you can actually schedule how and what order you want the experiments to occur. All right, so let's get more into some of the key resilience practices. This is where we're going to get more into chaos and game days. So let me back up here for a second. So the way I look at the field of chaos is being a part of the resilience practice. Okay, so it's more than just testing your individual components and seeing how things respond. It's also about just finding out, is your entire team able to respond to these issues? Because it's not just about seeing that something broke, figuring out how you respond to that one thing with a technical fix. It also could be, let's say it happens in the middle of the night, and the person who gets the information, do they have what they need to be able to respond? Are they trained to be able to do what they need to do? It's a lot more than just follow these steps to fix the problem. And especially if there's some sort of cascading effect that affects more teams. And so that's why I put here, like, what are the steps to, or the key practice for resilience rather than just chaos, because it's more than just the chaos. It could be, for example, game days, which I'll talk about a little bit more in a minute. And if you're doing a game day, or even if, for just real life, you should have some sort of disaster recovery plan, right? And so that becomes more about it on the technical side, and then on the people side, there's more about the team culture building. So first, let's talk about chaos engineering and game days. All right, so some things you probably already know is that if you're confident that your processes work, and that if you're to deploy your application more often, you're going to do it more often, right? If you're not worried that you're not prepared for a failure, for example, okay, you'll deploy more often. The other thing that happens is if you deploy more often, then you also know that there's more perceived risk. All right, even though I think the evidence proves that when you deploy more often, there's actually lower risk, there's still that fear of pushing the button. And so if you know that you're prepared for some disaster, and you know that you have a plan for recovering from it, then you're going to feel more confident and you're going to go faster. Okay, so I call it swinging for the fences. All right, if you feel good, if you're a baseball player and you're confident in your ability to hit the ball, you're going to swing harder. Because if you're not so confident, you're going to try to swing slower so that you can kind of watch the ball coming in and get your bat on the ball, and you're going to go for a single or a bunt. But if you're confident in your swing, you're going to swing harder, and you're going to go for the fence. And I think that that's the same, that analogy I think works for me on deployment. So you're confident in your ability to deploy, you're going to deploy more and more often. And you're going to get more done. Your company's going to move faster. But you can't do that if you're worried about the failure. If the failure isn't something that in your head you have confidence in recovering, you might start swinging slower. Which, again, I think actually evidence proves actually creates more problems. Okay. And by the way, just as a backup here, for those of you who are a little bit newer to this subject, let me ask the audience here. So why would deploying less often be likely to create more problems? more changes, but go, and those are both the right answers, but why more change? More changes what? Per release. Right, so more changes per release. And when you make more changes per release, there's more dependencies, right? And from my own personal experience, I remember having a situation where somebody came to me and said, hey, we ran into a bug in something you wrote 4 months ago. And so not only is it that you get more bugs or more errors, but then the developers have to go back and remember, like, what was I doing then? Like, I don't even have that environment anymore. I've got to go figure out how to set that up. So there's just so many other issues that pile on and cascade to waiting to deploy. So I just want to make sure those of you who are maybe newer know that. All right, what did I leave off here? This is about where my slide's getting a little bit wonkier. All right, so let's see. Okay. So there's a book that's out called Accelerate, and basically one of the quotes that I liked was that build systems that are designed to be deployed easily can detect and tolerate failures and can have various components of the system updated independently. I think this just goes without saying, but one of the nice things about having these pieces work more independently is you have less of a effect upon each other. Immediate effect. But you still, even though if you do this as a best practice, you still need to test the entire system, because there are times when perhaps, for example, a system goes down and you don't notice the immediate effect because there's a queue somewhere, right? But now that queue is starting to back up. And at some point, that queue might get to a point where it fails. Or, it doesn't necessarily fail, but the backup is so long that there's never going to be a recovery, all right? So, even though those systems might be completely independent, that failure is still going to occur, because they're not completely independent. Also, this is another quote I like, which is, people keep talking about platform engineering taking over DevOps, right? This is kind of like one of these things where it's like the pendulum keeps swaying one way or the other. And so, pro tip, every time someone explains to you that DevOps is just CI/CD, basically just tools, right? One way you can explain to them really quickly that it's not just about tools, ask them how game days fit in, right? Because a game day is you're responding to a failure, and even CI/CD, the best CI/CD platform on the planet is still gonna have failures, and you have to have people understand what the hell's going on so they can recover from that. So yeah, if you're not dealing with that kind of part of DevOps, you have partial DevOps. That's another thing we're coining today, partial DevOps. No, I'm just kidding. All right, so what is the best way to understand your system? All right, science. Science is the best way to understand your system. And chaos engineering is essentially science. All right, so you're basically going to purposely run an experiment and see how it turns out. So let's look out the basics here. All right, so first of all, as I said in the title, chaos engineering is a feature, not a bug. In other words, you're planning this, and you're not waiting to find out. Okay, so again, kind of like a little bit of a summary here, but I wanted to reword this because this was not my original material, but but basically these are the 4 steps. Okay, so you're going to carefully apply these failures with an explicit hypothesis, and this is the science part of it, right? So you come up with a hypothesis, and then you go test your hypothesis. All right, so then you also want to start off with a small blast radius, right? Now they'll tell you that when you're about ready to do chaos engineering, some people will say, well, I'm not ready to do chaos engineering yet. Well, and the answer is, the question should be, well, why not? And they're like, well, I need to prepare for that. But that doesn't make sense, because the chaos engineering is what helps you identify what you need to prepare, right? Or what you need to fix. However, you probably shouldn't just run experiments without much thought because the blast radius, I mean, you could take down way more than you had intended. Okay, so you have to start, we would all recommend starting small. And then you got to communicate, of course, to who is going to be impacted by that, right? You don't want to run an experiment on something in production that's going to impact folks who aren't ready for that. And they need to have a well-defined process, and that goes without saying. So when this occurs, who's ready for the problems? Some problems are not going to be anticipated. We need to be ready for unanticipated issues. Okay, so in a nutshell, can't really read this here on my screen. I'm just going to walk over here and read it off of here. All right, so in a nutshell, you're going to select the experiments that you want to run. You know, you might specify a particular region goes down or something. Then you're going to run those experiments on a targeted system, which could be production. It could be your, by the way, does anybody know in a blue-green deployment which one is first? Is it?
Yes.
For sure?
Yes.
Okay. Because I think when they first came up with it, I was reading when they first came up with blue-green, and I don't think they had chosen one in the beginning. They were.
That's why it's blue.
That's why it's blue? Okay. So I was reading that about how they came up with it, and they're like, we just wanted 2 different colors. But I do like that idea of having blue be first. Because green feels like the newer one, right? Yeah, okay. What's that? It is, but I'm telling you, if you go back and read about it, they didn't choose green because it was green. But anyway, it doesn't matter. I'm going with what you said. I think that's right. All right, so you could choose your targeted system, and again, a blue-green environment would be a great one to do. You can observe the results in that targeted system. You want to learn from them, okay? And then you want to select the systems to, you select the systems to test first. And then you run your experiments. Okay, that's a little bit out of whack. All right, so you're going to apply the scientific method, but how? All right, so have you guys ever tried to teach what the scientific method is to other people? I did it with my 11-year-old. It was kind of interesting to teach her. She was learning it in school, but you know, when you're learning at school, I don't think they have a real world issue to deal with, and so. I was just trying to give her let's come up with a hypothesis, right? And it's kind of personal, so I won't get into it, but it was highly entertaining because when kids come up with like the craziest results, right? They don't have any real world experience, so they come up with results that are just completely unbelievable. And it's fun to test because obviously those things don't happen. My daughter's a little bit on the fearful side, so we applied it to something that she was, dealing with in sports, and we were able to prove that it's not as scary as she thought. Right? The world didn't end when she tried it. So, but in your real world experiments with your team, you're going to come up with a hypothesis, and. So first, you want to be able to measure how the system changes during the experiment. It's important to understand how they behave now. So that's the first thing you need to do is document like what is happening right now, so I'm comfortable understanding what I should be expecting. And so you want to come up with some baseline metrics. It could be just something like response time or whatever, but some baseline. Then you want to think about, okay, does this actually work the way I think it's going to work? Like, I have some assumptions about how this should work, but let me actually be thoughtful about this and understand how this system actually works. And then you need to actually go and validate that, okay? Because you're guessing, most likely, unless you're the one who built the system. So you need to go and validate, is this actually how it works? And then you can start thinking about what kind of failures could I inject to help me prove that it actually does indeed behave that way. So one of the things you could do is simply run experiments to prove that the system behaves the way you think it does. That's an excellent place to start. okay? Because if you don't truly understand how the system behaves, when you run your experiments and you get the results back, it is really hard to understand what the impact was. What was the meaning? What are you now going to go and fix and change? So you really do have to understand how it behaved, or how it actually works. By the way, I was just in one of these sort of like think tank type sessions. You know, I don't know how to explain it. It's just a group of people who are paid to sit in a room and answer questions about things. My specialty is how different platforms have evolved over the years. And one of the topics they brought up is how do you innovate? Okay, especially in an established industry. And the one solution that was proposed that I liked was you get your product, which could be your application, and you get the people who know the most about it in a room, and then you document every single step of the process, every single one. And it's exhausting. It could take a week, all right? You document every single one, and for every single one you ask, do we need that? Is that necessary? And you're ruthless about it. And in this process, you'll probably eliminate some stuff, and you'll probably come up with some ideas about innovation. But you could just do this with your own engineering team and your own application to understand what's happening so you can then design experiments. And I was thinking about this in the context of this talk, and by the way, are we almost out of time? No way. Okay. Oh, jeez. Okay. Sorry, I've got a lot more slides, but okay. So with the context of this talk, I was thinking about how you go about designing a game day and why you're going to get people together to do this. And simply understanding how your system works is a great benefit. You're going to come up with parts of your process you can eliminate or improve or innovate. All right? We do CI/CD. You know how many steps are involved in CI/CD? A lot. But if you think about how you can eliminate them, one of my projects in but as soon as I change it to, how about the 10-click deployment project, people are like, oh, we can do that, right? So it makes you think differently. Okay, so anyway, let me move along here. So you got to understand your blast radius of the experiments that you've chosen, and make sure you set abort conditions, all right? Because things could totally get out of control, and you better have a plan for that. And then analyzing the results. And then sharing the results, okay? If you're involved in DevOps, you should know sharing is a very important part. So that's basically the steps. All right, so again, there's a cycle. There's also a great Netflix ebook out there. If you email me, I'll send you a link to it, which goes through a lot of this in a lot more detail. And one of the things they say that was different than that I listed, which is what we came up with, was that you start small, but then quickly increase the scope, because small may not be useful. Big is useful, but you have to be careful about how big you go. But if you quickly increase the scope, you should be able to get there pretty quick. And so, of course, automation is very important. Right? You want to be able to automate this. Some people actually have this as a part of their CI/CD pipeline. So it's actually something that they're doing every time. They're running these experiments every time. Because if you're big enough, your application is big enough, more teams, you don't know what's actually changed. And so you can't actually think holistically, oh, that changed, I better change, now I need to run that experiment. You might just need to run them all the time. It's kind of like a build process with your continuous integration. All right, so I'm just going to give you a quick screenshot here of the different types of experiments you might do if you're using chaos, for example. So we call them experiments. And these experiments are now becoming broadly adopted, so beyond just chaos, beyond litmus chaos. For example, AWS has now started to use litmus chaos experiments as a part of their FIS service, okay? So these kind of experiments are not just useful if you're using litmus chaos, but they're also useful if you're going to use AWS fault injection service. All right, I know I'm out of time here, but okay, so if you want to contribute, please contribute. Go check out our experiments, and if you want to contribute to one of them, you might find it somebody's running it in AWS, for example. All right, for a quick demo, so there's a how many of you seen the Bank of Anthos sample app? Anybody? Okay. Well, it's a really good one. It's created by Google. There's lots of reasons why it's good. I'm going to skip that right now. But basically what happens is, this is a very simple example where you have an application, and here's all the dependencies. Very, very simple example. Banks. Banks have outages too. Now, they usually have them all separated into individual components. One of the services might simply be a balance service, okay, because you're using that balance all over the place, right? What if the balance service goes down? Okay, pretty simple example, okay? So how does this actually work? I don't know how other projects work, but I know how Litmus Chaos works. What they basically are doing is they're putting a proxy, and that proxy is in between every communication between systems, or between components. So everything's going through the proxy. And so if you're making a call to the to the balance service, you can set up an experiment that intercepts that request and responds as if it would if it had failed. Okay? And so that's essentially what's happening in these chaos experiments. They're intercepting the request and they're responding as if it had failed. And this is even for databases. Databases are starting to get slow. It'll actually intercept the request and have a timer, and then respond. And they'll set it up so it's slowing down over time. And so you can actually see what happens if your database is slowly getting slower, okay? In this particular case, it's just a failure of a service, and so you want to be able to respond. You don't want your whole application to go down. You probably don't want to put like 3 dashes or whatever that is, right? So you're going to set it all up so that now I know if that's down, I don't want my page to break. I don't want the dashes. You're probably going to want to put some better information there. In fact, you don't want them to be able to stop. You don't want them to have to stop doing other work. And I happen to know that banks cache this piece of information because when I was at Redis, one of the things that was interesting is a lot of banks they didn't want to replace Oracle, but that morning when everyone checks your phone to see your balance, they have this huge spike like around 9 a.m., and they just wanted to cache all that. So they just take all that balance, what your current balance is, and they put it in memory. And so that would be a good use case. I should share this with my Redis friends and say, look, you should run a chaos experiment, and then they should use Redis to cache that balance so that even if it goes down, they're still going to be able to see like that amount. And what would you do? You would say, here's the balance. You don't just leave it at that, because that could be very out of date. So you would say, here's the balance as of this time. Okay, so therefore you're protecting yourself. But that's the kind of thought you can go through, is if you understand how the systems are working, and you understand what's happening behind the scenes, now you can come up with a hypothesis, you can test it. Can a cache actually solve this problem? It can, but wait a minute, what other issues are we dealing with? What about latency? This is no longer the accurate information. Just put up the right, that additional caveat, this is as of this time, and now maybe that works. Okay, so there's obviously more experiments you can do. All right, I'm over time, but let me just take one minute here. I was going to talk more about game days here. So game days. Game day, you're basically doing this in a protected environment. You can do it with production as well, but usually you're going to set up a protected environment and run through this whole process with your team. What I wanted to share with you, just real quick, and if you want the notes to this, this is from Karthik is the co-creator of Litmus Chaos. And I can't really read this real quick, but I just want to share with you these thoughts, okay? Because these are like from actually running game days. All right, so obviously define your radius. your blast radius. Define the failure so there's minimal damage. So you kind of can guess what kind of damage there will be. So start off with minimal damage. Try to do one variable at a time, because then when you get the results, you know that the result was because of that one variable. That makes it much, much easier to then go and correct. Use the scientific method. All right. Simulate as many real-world problems as possible. Here's some examples. Resources. These are like the popular ones that he knows that came to his mind. Resources becoming slow, noisy neighbor. You're on a server. Maybe you have multiple of your own services running on the same physical machine. All right, noisy neighbor can eat up resources. Availability zones may go down. Instances may become unresponsive. Sudden shutdowns. This is one that I think everyone should be testing for. Black swan events. Oops, misspelled that. These are hard to come up with. But it's a great exercise to think through, because sometimes you'll identify what you thought were black swan events that are not black swan events, right? So it's great to think about those. Buildings going down, regions going down. AWS will tell you where their regions are. Google does not give you that much information. So if you're on Google, you may need to do a different type of test. If you can, test in production, because that's where the most unknowns are, right? That's organic, right? People, traffic, all those things you don't have in a test environment. Try to repeat them continuously. You don't know what's changed. Automate tests so that you can, okay, this is, I think, probably one of the most important things to do. Automate the tests. Okay, it's super hard if you can't reproduce what you did. So you got to automate the tests. And just keep in mind, I want to end on this thought, which is that human beings are most likely the cause. Okay, that's just the way it is. We're out there mixing up with these systems, and we cause a lot of problems. But this is something that Julie said, so I want to share this with you from her. We have compassion when a system goes down. Like, oh, the system failed. Okay, right? But when a person makes a mistake, we don't necessarily have that same compassion, right? And I think we should. I think Julie says it, and she thinks that we should. I agree with her. So I'm not necessarily saying how you deal with that, but blameless culture perhaps, think of that way. If it's blameless, people are going to be more likely to come forward and share what caused the problem as well. So I think I would leave you with that, is that when you do these experiments, I think it's a great team building exercise, and you'll find out that, oh wow, that person's really dealing with some complex stuff. And maybe you can have a little more compassion for them when it goes down. Or even something simple, because sometimes the simple things are things you overlook. All right, that can happen. Just have more compassion for the people you're working with. Thank you for staying over time. I appreciate it. And if you want, I have my slides. Hold on a second. Yeah, here's my contact information. Feel free to email me or get me on Twitter, and I will make sure you get the slides. Thank you.
Okay, let's get started. My name is Simeon Army. I am a production engineer at Meta. I work with the Artificial Intelligence Group. I'm going to be talking a bit about chroot and proot. So I'm a production engineer. That means I work on the reliability, scalability, and efficiency of the systems at the company. In particular, I work on artificial intelligence systems, both like training new machine learning models and deploying machine learning models into production. I don't work on the containers team, who would be the people who have expertise on like chroot and the topics that we'll be covering today. I just think they're neat. Production engineers at the company tend to have a very wide breadth of experience, and if it comes in handy that you happen to know a little bit about containers, then it can be really useful on the job. For example, working in AI, I had a use case where I needed to isolate certain GPU devices from inside a container. So one container would have access to some GPUs, a different container would have access to a different set of GPUs. And this was just something that I learned externally on my own, and it came in handy in my job. So we're going to talk a bit about chroot, what it is, what it does. We're going to have a lot of demos and examples in the talk, so hopefully the demos go well. We're going to quote unquote accidentally forget the password on forget the password on a Linux machine and then go and rescue that install, changing the password for it. I'm going to pull out an Android phone and run some standard Linux desktop style applications on it. So we're going to play around a little bit with Android. We're going to use proot, which is a slightly more flexible version and like user space version of these utilities, to fake some stuff in the OS, including pretending that we have a different CPU than what we actually have. So I have on a USB drive a file system from a Raspberry Pi, and we'll be running some programs, even though the Raspberry Pi has a completely different CPU architecture than what's in my laptop. And then at the end, we will cover a little bit about containers and what they do. So containers are really great for isolating applications. You might think about a virtual machine as a more general version of a container. What a virtual machine differs from a Linux container, the kind of isolation that we're going to be talking about, is that a virtual machine has to load an entire operating system. If we're running a Linux application, then we can just tell Linux that we want to run a Linux application without having to load another copy of Linux in a virtual machine. That's a container. Containers are also really useful for deploying software, so you can just ship an entire OS inside a container. But let's just dive right in. So chroot. Chroot or chroot, I've heard both pronunciations. I have no idea which one is correct. This isolates a program to a particular directory. It changes the root directory, chroot. And we're just going to dive right into examples. So what I'm going to do is I'm going to create a couple directories. I'm going to create a temporary directory and a bin subdirectory in there. And I have an application here called BusyBox. BusyBox happens to be a self-contained version of a lot of the standard utilities you might find on a system. I'm going to copy that into my directory here. And I'm going to chroot. I have to be root in order to use the chroot utility. I'm going to change the root directory to be temp. And then I'm going to run BusyBox inside of that temporary directory. It's now going to be /bin/BusyBox. And I'm going to tell BusyBox that I want to run a shell. So I am now in a chroot environment. The only things that I can see in this environment are what's inside that directory. If, for example, you were running a file server, you would probably not want that file server application to be able to access all of your system. You only want it to be able to access maybe a user's home directory or a web directory. chroot is a nice way to restrict that file server's ability to access the rest of the system. So what can we actually do with a utility like this? Well, I built a small, probably the minimal environment for running chroot, which just contained a single application. We could chroot into an existing Linux file system. So what does that look like? I'm going to start up a virtual machine. This is just for the purposes of the demo. You could be doing this on physical hardware. And please feel free to interrupt if, for example, something I'm doing on the screen isn't particularly visible. So I have a demo user account on this machine. Password is just demo. I'm going to log in and change the password for this user. Just going to do that with the console, with the command line. And let's go ahead and create something that's going to be a very secure password, like blah, 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 blah. I'm going to just paste that. Oh, the current password is demo. Let me clear that out. And paste in the new password. And log out. And now if I were to try to log into this account again, I am not able to. If this is the only account on this system, I would be pretty screwed. I would have to go and maybe reinstall the operating system. Like, how would I access my files? Let's reboot into an install environment. So this happens to be the Kubuntu installer on a USB drive. I'm just booting into that USB drive. And testing out the environment, so I get a regular desktop. So there are a couple things I have to do in order to gain access to the actual system on this machine. So I have a CD-ROM drive. That's the live CD that I have plugged into this virtual machine. And then I have the disk that's built into the system. So I need to mount some of this. I happen to know, let's create a directory to mount this to. And I happen to know that the file system, the root part of the file system is dev sda2. So I'm going to sudo mount that to dev sda2 to mount target. And now if I list out mount target, we have all the files from the system. And if I look at it in the File Explorer, this is the basic file system on this machine. So I could run applications if I chroot into this directory. So sudo chroot into mount target. And now I am on the file system of this physical OS. If I look at /home, I can see that there are the two users that existed on the system already, and I could run a simple program like password demo and type in a new password. I'm just going to make it demo again. And now the password has been updated successfully. I have, if I reboot the system and log in as demo, we should be able to log in using just the password demo. If I wanted to do more complex things, I could mount some supplementary file systems. Say, for example, if I wanted to install some applications or like fix a grub configuration, or maybe I made an edit to FS tab that I shouldn't have. Let's add a little bit more into this environment. So there are some support file systems that will be important if you're running an entire OS inside of a chroot. I'm going to mount bind. This will make a part of the file system available in two different places simultaneously. So the special file system dev contains all of the, for example, disks that are attached to a system, as well as a whole bunch of other stuff. So I'm going to make that available as mount target dev. In addition to that, I'm going to do just some other ones, proc, which contains information about processes that are running in the system, and sys, which has some configuration options and information about other devices in the machine. So now this is actually a fairly complete system. I can chroot into that system. I could do update grub, and that will like reinstall or reconfigure grub if I needed to make changes there. If I wanted to install some packages, I have to do a couple additional things. So one of the relevant configs for accessing websites on the internet is DNS. That happens to be configured in etc. Resolve.conf. At the moment, resolve.conf happens to be empty. I'm just going to make a backup of that. Resolve.conf to resolve.conf.back. And I'm going to write just a name server. This is a DNS machine. 8.8.8.8 happens to be Google's public DNS. I'm going to put that into resolve.conf. And now, if the Wi-Fi is being cooperative, I can apt update, I can apt install new applications in this environment. So apt install, let's do CMatrix, because that'll be a fun little demo. And that's installed on the actual physical machine. It's not installed in the live CD environment. So I can exit, like CMatrix is not installed on the live CD, it's installed on the physical machine, and let's just reboot. So we're going to see two things when we boot into the original OS. We're going to see that the password for the demo user is returned to normal, and we're going to see, hopefully, that chroot, or that CMatrix is installed and accessible. Taking a little while to restart. For the sake of the demo, I'm just going to hit the reset button. Don't do that on a real machine. So now we have the demo user. DEMO is the password. That worked. And the program that I installed, CMatrix, is now available inside this environment. One last thing to do, since I renamed resolve.conf, would be to rename this file back to what it originally was. Remove the one that I customized and put the original back. So that's just one of the really cool uses of chroot. Another really cool use is on an Android device. So let me plug in my phone and open it up. Cool. So what I'm going to do now is I'm going to grab Ubuntu Base. Connect to my phone so you can see what's going on. Okay. So we need, if we want to run a desktop Linux OS on a device, we're going to need to download a version of it. The installer is going to be basically no installer. We're going to install it manually ourselves, but there's a few really simple options for doing that. Ubuntu happens to offer Ubuntu Base, which is just the file system in a tar, in compressed archive that we can just directly download and use on the phone itself. have pre-downloaded a relevant image. This ARM64 is the CPU in this phone. So we're going to open up a terminal. And I have to be root to do this, because chroot needs a privileged user in order to run. So we're going to data media. Cool. So I have the commands on here. It's worth noting that these slides are uploaded to the SCaLE site, so you will be able to access this after the convention, and I'll have links to relevant documentation at the end of the presentation. So don't worry about copying too much of this here. So we're going to just make a new directory for our Linux install. This is chadder is something I had to do on my personal phone that I have as a rooted device. Some operating systems care about whether capitalization matters. Some operating systems don't. Most desktop Linux environments care about the capitalization of files on the file system. Some file systems give you the option to toggle that ability on or off at will. So what I'm going to do is just make sure that case sensitivity is enabled on this directory with chadder-F. And now I'm going to extract the Ubuntu file system that I downloaded. So that's just tar with all of its complicated options. The SD card happens to be mounted on this device in data media 0. So download Ubuntu base, and I'm going to -C extract it to a directory, the Linux directory. So I am now quote-unquote installing Linux on this device just by extracting the file system. And again, similar to what we had in the live CD environment, I need to add supplemental file systems. So mount bind /dev into Linux dev, and similarly for proc and sys. And now if I chroot, I'm going to be running, rather than just chroot without any program specified, which would give you a basic shell, I'm going to be running login-froot, which will set up more of a standard login environment. chroot tries to preserve some of the stuff from your original environment. So chroot Linux, and I'm going to run bin login, and the user is root. I am now running in an Ubuntu Debian derivative Ubuntu environment on the phone. I can run standard phone applications, standard Ubuntu applications like apt. Let's apt update. This is going to fail with a lot of errors, but apt is running. So let's actually fix those errors. So again, we have to set up DNS. So let's echo the 8.8.8.8 name server into resolve.conf. That's still not going to give us full network access. Any application on Android that wants access to the internet needs to be added to the inet group. This being a standard Ubuntu install, we don't have the Android groups or users in the environment. So I just get to add that. So group add, number 3003, Android inet. There's also an inet raw, which we don't actually need right now, but if you're setting up other users, you might need it. I'm just going to apt downloads applications or packages as an unprivileged user as a security measure. So we need to add the apt user to the, we need to change its primary group to Android inet. And now we are successfully downloading the packages list for Ubuntu. The underscore is part of the username for this user. Underscore in some programming languages implies that it's a private or inaccessible variable. This is analogous to that for the users list. They just prefixed it with an underscore for the apt user. Cool. So that was chroot. It's a very powerful utility. Let's talk about proot, which is basically a debugger. Proot uses ptrace under the hood. I'm just going to move that out of the way. Proot uses ptrace under the hood. It's a utility for debugging applications that doesn't require elevated privileges to run. Proot gives you the ability to do things that are very similar to chroot, mount bind. We've used both of those in the previous examples. And they can also do a functionality called bin format, which we'll get to in a couple minutes. So one of the really cool things with proot is that we have the ability to bind files or directories without being a privileged user. So lsb release is a command which tells us information about there we go, lsb release -a. It's a command that tells us information about the operating system that's currently installed. How it actually works is it reads a file in etc. In the case of this machine, it's Red Hat release. Contains the name of the OS and its version. Say, for example, I had a program that checked what version of the operating system it's running on, and you want to run this on like a newer operating system. Maybe you don't have access to the source code of that program. Let's give it a slightly different view of the file system. So if I copy this Red Hat release file into my current directory and edit the file. Let's change it to, I don't know, not Fedora release 99. There we go. And now we're going to proot. -b is analogous to mount bind, and we can do this with files as well as directories. So we're going to take the Red Hat release file and we're going to make it available as etc Red Hat release. And we're going to run lsb release -a. And now, as far as lsb release is concerned, we are running not Fedora release number 99. proot also has the ability to do a chroot like thing in an environment. So I happen to have another version of Ubuntu Base here, which is basically the AMD 64 version, which is compatible with this laptop. I can proot -R. This is a shortcut which adds all those like dev, proc, and sys to the file system for us, so we don't have to worry about that. And I'm going to do that into the Ubuntu base directory. And now I am in, as though I had chrooted into this environment, I am in the Ubuntu base install. But I am not a root user. I'm just an ordinary user on this system. Okay. So let's do that with a slightly more exotic machine. I'm going to plug in the disk from a Raspberry Pi. I'm just going to mount it. And this happened to mount where? Let's go here. This happened to mount in run media SAE. So let's go there. Run media SAE, and rootfs happens to be the Raspberry Pi environment. Now, if I were to just try to chroot into this, that would normally give an error, except that I have a few additional packages on the machine. Let's do this as, so let's first establish that I am running on an x86-64 machine. Now I'm going to sudo, let's just do the regular proot. Again, as adding all of the additional file systems that we want. I'm going to do that, and I'm going to add this utility, user bin qemu arch64, because this is a 64-bit image, static. So QEMU is an emulator. It lets us run like a virtual machine of a different CPU. So we can emulate an ARM CPU on an x86 machine. We could emulate an x86 machine on an ARM CPU. This particular utility is QEMU user. It will translate individual programs. So we can proot into this environment, and now if I uname-a, as far as the applications in this environment are concerned, I am now running an ARch64 CPU. And like I have utilities that are available on a Raspberry Pi, like Raspberry Info. So I am now in a Raspberry Pi environment, even though this is a completely foreign set of binaries to this machine. If I wanted to enter this environment as a privileged user, a slightly different set of options is helpful. So -S sets up a shorter list of convenience mounts for us. And I can do the same login -f root. What did I screw up? Oh, I need to be a privileged user. And I happen to have proot in that location. So I'm now a privileged user on the Raspberry Pi file system. I can apt install, let's do CMatrix again. And let's do xterm, because that's always a fun demo. So that's going to take that's going to take about a minute. Do we have any questions in the audience at this point? Go ahead.
You mentioned ptrace when you mentioned proot. Is there something going on here that's using ptrace?
Yes. So proot is attaching a debugger to the application that we're running. In this case, I'm running the login program. proot is attaching a debugger, and then it's monitoring all of the system calls that the application is running, and it can modify the output of those system calls. So when the program needs to execute when it needs to list a directory, we can modify the results of that list with the debugger. That's how we, for example, change the Red Hat release file. Anytime the LSB release application listed out that file or tried to read from that file, proot intercepted that call and changed what the application saw.
What Dutch Q did you recommend? You wrote that R.
Oh, yeah, -q. So this is how you specify the emulator that you would like to run. So -q with the QEMU arch64 static, that will run the binaries inside of an emulator. And that -q specifies which emulator you would like to use. Yeah?
You said -R mounts like dead and proc and sys, and -S. How much of a smaller list is S?
Yeah, so the man page for proot has the complete list, but -R adds quite a lot of additional convenience mounts for you. So this includes like resolve-conf, so we don't have to do that when we use -R. It also mounts your home directory inside the environment. So all of the files that you have, like your configurations in your home directory, are also available in the isolated environment when you use -R. And when you use -S, you do get a much shorter list. So the -S option is a little bit safer for package managers, so you don't, for example, change the time zone on your physical machine when you're changing configurations in the environment. Yeah.
Are all those paths mounted read-write, or is it just like read-only?
So the paths with both of these options are theoretically read-write, subject to the regular Unix permissions. So an unprivileged user is not going to be able to create new files in /dev.
But the changes will be reflected.
Yes. So bind mounts are like making this directory available in two places at once. So any changes that you make to one are changed in the other, which is why it's important to like not add too much stuff from your base environment into this isolated one. Cool. So that finished. Let me go back to logging in as the unprivileged user. I can run xterm. Now xterm is running. The AArch64 version of xterm on the Raspberry Pi file system is running on this machine, and I can run cmatrix inside that environment. So people like to say that everything on a Unix system is a file, like everything is a file. And to a large degree, that's true. But there are also a large number of shared resources on a system that aren't isolated when you use a tool like chroot. We're talking about things like how much CPU is a program allowed to consume. When a program accesses the network, that's also a shared resource. Like every program has a similar view of what the network devices look like. So what do we do if we want to isolate some of these shared resources? We have two major tools for doing this. One is namespaces, which I'll cover now, and the other is cgroups, which I'll cover in a couple minutes. So namespaces control what things are visible, and cgroups control how much of the resources we're allowed to consume. So we mostly looked at what mounts are available when we talked about chroot. We can create a namespace for these mount points. So that, for example, and I will actually just dive right in, we could provide we can provide an isolated idea of what things are even mounted right now in a file, in a chroot-like environment. So if I bind mount something in an environment, that is visible to both the external environment, the base that's on the system, and it's visible inside the chroot. But if we're in a namespace, then the things that happen inside the namespace stay inside the namespace. So I've got this pre-typed. I'm going to run unshare with also the, I'm going to do the PID namespace. So another shared resource is what applications are actually running. So if I run, for example, PS with a whole bunch of options, we see there are lots of programs running on this machine. So if I were to unshare is a command line utility which lets you interact with namespaces. I'm going to unshare, and I'm going to play with the PID namespace, PID, process IDs. Fork lets us run an application, and I'm going to use the same Ubuntu base as before, except I need to be in my directory there. Okay. So this did a couple things. If I PS again, now there are only two things happening inside this environment. The two applications that happen to be running were bash and the PS command that I ran that generated this list in the first place. And I forget, did I do the, well, let's try this. Let's mount a new dev in this environment. Let's look at the... Okay, so we have two things going on right now. I just mounted, inside of this unshare environment, I mounted dev. So this is a fresh new dev mount point. If I list /dev, we have a whole bunch of interesting stuff happening inside of that dev directory. But if I look at the equivalent path outside of that isolated environment, we have basically nothing happening inside that directory. So the things that are mounted inside of the environment are different than what's visible on the system outside. That's kind of what you get when you use namespaces. And there are lots of different kinds of namespaces. I talked about mount, I talked about PID. You can also have an isolated view of the user IDs on a system. You can have an isolated network environment so that the network configuration inside the now container can be different from the network configuration on the base host. So that's a basic introduction to namespaces. Now we'll also talk about C groups. So C groups are a little bit complex to play with. There are two versions of C groups that were implemented in Linux. There's C group 1 and C group 2. C group v2 is the default now on most desktop Linux distributions, including Fedora, which I happen to be running on this machine. And C group 2 makes it easier to manage multiple resources at once. So all of the example here is going to apply to C group 2. So C groups let us control how much of a shared resource we're allowed to consume. This includes CPU, like what percentage of CPU utilization we're allowed to run inside of a C group environment, how much memory those applications are allowed to use, even more exotic things like how many processes this application is allowed to spawn. But let's play with it then. So if you don't already have C groups set up, you can just mount it. It's a C group file system. But this happens to have it already configured out of the box. And C group 2 happens to be mounted on sysfs C group. So we're just going to hop into that directory. There's a whole bunch of stuff that we can configure here, including there's a lot of different C groups pre-configured on this machine. But we're going to do our own from scratch. And how this works is we just create directories, we write short contents into files. It works in a very simple way if you're used to editing things on the command line. We can also change the permissions on the directories and files in C group if we wanted to give an unprivileged user the ability to change the limits within this environment. You can create subgroups inside of this as normal directories, so you can delegate some amount of resources to a user, and then they can subdelegate a subset of those resources to additional applications that they want to run or constrain. So let's actually do a demo. This will be fun. I'm going to let's load up top so we can see the CPU utilization on this machine. I'm just going to move that down to the bottom. Okay. Now, let's just run a program like stress ng-c0. Except I need to be in my home directory to run that. So stress-ng is a benchmarking program, or rather a stress testing program. It's going to load up all of my cores. We can see that basically all of the cores available on this machine are effectively fully utilized. Let's try and constrain the resources stress is allowed to use. So let's cd back into sysfs C group. And let's make a new C group. We're just going to call it demo. And now I can, that is now just a normal directory in here. We have a demo directory. And when we cd into that directory, we're going to see that magic happened. there's now a long list of files that were automatically created for us in this directory that will let us configure this C group. So there are a couple things that I need to do in order to get an effect from C group. One is I need to configure a limit, and the other is I need to define like what stuff should be restricted. So let's handle getting the stuff that should be restricted. So what I'm doing here is I'm running pgrep stress. This will print out the list of all of the process IDs for the stress program that's currently running. And I'm just going to write all of those into a file, cgroup.procs. So what this does is it adds all of the processes that stress launched, it adds those to this demo C group. I'm also going to take the process ID of this shell that I'm currently running and put that into the C group as well. So now we have in this C group procs file a list of the process IDs that are inside of this C group. So there's also resources that we constrain, CPU.max is one that's particularly fun, considering I'm burning the CPUs in my machine right now. Let's see what that looks like. It's just a file, and it's telling us, and this is in the documentation for C groups, that it's allowed to use the maximum available CPUs for every 100,000 time slices. We can edit this. Let me just write, let's make that 100,000 out of 100,000. I'm just going to write that into the file. And what we should see happen is that the CPU utilization now drops down by a lot. So 100,000 divided by 100,000 is 1. And so the total amount of CPU that all of these processes as a group are allowed to consume is 1 CPU. If I wanted to allow it to run maybe 2 CPU cores worth of compute, I can just change that to a 2. And now it's allowed to consume 2. There are 16 cores in this machine, so this should be roughly equivalent to max. And we can see that reflected on the top graphs below. We can also greatly restrict the amount of CPU that it's allowed to consume, like that. That's 10,000 out of 100,000. So now everything, including this shell, only gets a very small amount of CPU granted to it. That's why pressing enter was very slow, because it's only allowed to use a very small fraction of a core. And if I kill the CPU stress, it's a little bit more responsive because it was sharing the CPU budget with stress ng. And any application that I run in this shell is similarly constrained. So if I were to run a new copy of stress, I have to do that from home directory. This new copy of stress is also constrained in the C group. So you can't just like get out of your resource limits by launching a new program. Cool. Those are all the demos that I had. I will take some questions. So if you have any questions, feel free to ping me. I'm going to leave a slide of additional resources up. So the slide deck is available on the SCaLE site, and it includes links to the documentation for chroot, proot, namespaces, and C groups, and all of that stuff. So these are the basics of like a Linux container environment. So if you're running something that looks like Docker or LXC, it's going to be using a lot of these kinds of tools to do that. So questions? Oh, that's because I ran it through sudo. So sudo escalates the privileges there. These utilities, you can do, you can change the user inside of the environment as well. So I could like SU to a different user when I'm in that environment as well.
Seems odd because I'm sure I'm thinking just wanted to change the namespace.
Yeah, so you
Namespace without changing the privilege level inside the namespace?
not as far as I know. Like, you need certain capabilities in order to create a new namespace. Those capabilities are available to the root user. They're not normally available to unprivileged users. The Linux capabilities framework can give a normal user the capability to configure a namespace, or you could have the root user create a namespace, go inside of that namespace, and then lower its own privileges to run as a normal user.
But is there a way to create namespaces, I assume, without changing into them?
Oh yeah. So there is a way to create a namespace without then diving into that environment. So unshare, like if you check out the documentation for unshare, you can get a lot more information about creating a namespace, like without the -- fork option. The fork option is what did that for me.
Can you talk a little bit about escapes from chroot?
Yes. So I've been using the chroot command line utility. It has the version that's in GNU Core Utils has a few safety protections available to it. So as far as escaping chroots, if you're using chroot is also available as a system call. So any application, like any C application, I think Perl also supports it. You can run chroot and then change your current directory, change your root directory. What happens then if you delete that directory? Like if you chroot into a directory and then delete that directory. Most Unix systems, I think, will actually let you do that. And so if you are executing inside of a deleted directory, what happens then when you cd ... that can actually break out of a chroot environment. So chroot isn't perfect as a security mechanism, and some of the modern OSs do provide guardrails in a utility like the Core Utils chroot. But that's where mount namespaces come in and are a little bit better, because inside of a mount namespace, you can completely change the visibility of the file systems that are mounted, and you can unmount things that the namespace should not have access to. Yeah, so the question was about when, in my example, I entered into an environment that was not encrypted. What happens if you have an encrypted disk? The short answer is you will need to decrypt it somehow. On a Linux live CD, like the Kubuntu installer or Ubuntu installer, if I were to just open up the file browser, like with Dolphin, I could click on a file system that's encrypted with, for example, Lux, and it will open up a prompt asking me to type in the password for that file system. If I know the password and I type it correctly, then it will give you a new device in /dev, and it will mount it. That will give you the unencrypted view of that file system, and you could chroot into that. Yeah, so the question is about why does the chroot command line utility require root permissions? That's because changing what is visible to a program gives you some additional control over the program. So you don't want anybody to just be able to do that. It comes from, I think, older Unix systems where the privileges were reserved for the root user. When things like proot exist today, it's perhaps not as useful a restriction as it used to be. But yeah, I don't know why it still has the same restrictions, most likely for backwards compatibility, so that we don't change APIs or add functionality to things that should not have that functionality. question is, do ACLs come through in a chroot environment? Yes, they do. So if you have a file ACL inside, attached to a particular file in a chroot environment, that would still be the same file ACL. Cool. Hey, thank you. Yeah. And finally, I will leave you with one additional thing, a question that didn't occur to anybody to ask, but like if you have to be root to run chroot, and I did my example on the Android device with a rooted Android device, what if you don't want to root your Android device? Could you use proot on that Android device? The answer is yes. So there are additional links there if you want to run a Linux environment on an ordinary stock Android machine. All right. Thanks.
Check.
Hello. Is it me you're looking for? I can see.
Check.
So, do you know any long stories that you want to tell? Do you know any story that lasts 8 minutes? Trying to find.
I waited so long, wouldn't want nothing. Don't worry, there's still raffles to win tomorrow.
Yeah, there is an art to do one. Hey, look, there's Metaphor there.
And the 3D printer, unlock the 3D printer.
Where's that? Oh, yeah, but that requires me selling myself to AWS. And I already do that for a
You
living.
just gotta get your badge scanned.
Oh, that?
That's right. It's the thing came off.
Yeah, and I have no ability to sample any of these things.
Signal to the AV people.
No, they just like correct. I'm surprised they did the thing here.
Self-service. Anyone can do it.
Yeah, it seems like I have enough.
I guess when it's my turn, I'll just reach my hand.
No, I will move, and I will do the finger guns. That's the art that we.
But you can push all the buttons for the demo.
Yes, the demo. I know. You can do it yourself also. I was gonna say, like, what we should have done is we should have installed this on your laptop also, in case the thing dies.
Well, I mean, I was prepared to give the talk. I have the Google Slides. But it's better this way. You have the handless mic, and I have the handheld.
6 minutes? Yeah, now in theory, everybody is here.
They have nothing else to do, so they're all There's some other tools.
Looks like we're having a full house.
Everybody loves System D, right?
Yes. Well,
Wish I had the shirt.
Oh, I should have worn it.
You have one? Oh yeah, you have one.
Yes, I have.
You have brought it, and then we just like put it right there. Right? Oh yeah.
Displayed it.
It would have been, but I forgot that today was the system detox day.
Well, this is for T minus 4 minutes.
Where's some of our other friends, though? These.
Hello? Hi. Okay, so we're going to get started. So everybody settle down, sit. I'm really surprised of having this room so full. Either people really like systemd or really hate systemd, and I can't really figure out. No. Not until the end of the talk. Okay, cool. So I'm Alvaro. She's Anita. We are here to talk to you about Journey to the Heart of systemd, right? And that's kind of like the sales pitchy or the clickbaity title. We're just going to do like an introduction of a little bit of what is systemd and what are the less known features of systemd, right? A small disclosure here is that both Anita and me, we both work at Meta. And even though in Meta we do use and abuse a lot of systemd, this has nothing to do with how we use systemd. This is plain vanilla systemd, and this is how you, in your own life, can use systemd. And by the way, if somebody's counting the times that we say systemd, at the end we appreciate it. Okay, so that's the Meta logo, in case you haven't seen it. And let's move on. Okay, so a little bit of agenda, right? So since systemd is mostly a service manager, let's talk a little bit about what actually is a service manager. And then let's talk how systemd fits into this space. Then we're going to do examples, which is basically going to be code, feature, how you used to do things before systemd, how you do it now with systemd. And then we're going to do a live demo, which is always fun because it's the thrill of doing it live. Cool. So with that said, let's just get started. So what is a service manager? Nothing fancy here. A service manager is something that manages your service, right? So in general, like you have Postgres. Postgres is your service. The service manager is the thing that makes sure that Postgres is alive, or Postgres is down, or that Postgres gets started before you start your web server. It kind of manages like the operations of your service. And by operations, we mean actually verbs, right? It also makes sure that your service like start and stop whenever it can. That's what we call lifecycle, right? So if there's people that is all here, you remember that in the good old days, did I struck a nerve? Well, I was there here. I was there for the final part. Okay, so well, in the good old days, you used to put like bash script into etc init. And nobody really knew why we did this. It just was convenient, and then we put it there. And that was our service manager, right? So you were your own service manager at that point. So you write stuff like this thing over here, which is, yes, and thank you very much, because this is the init script for Cassandra. It's taken from for Debian, right? So here is one of the things, right? So in this script, you would define verbs. And this is just a shell script. So your verb is basically how you decided to parse the command line argument that you pass to the script. So you have start, stop, restart, and force reload. And here the first thing that is wrong with this approach, or like we did not like that much, it was that these verbs are not transferable from one service to the other. So you can name something start, and you can say something go, and that is not transferable from one service to the other. Also here, restart and force reload are the same thing, but I'm pretty sure that in a web server you don't want that. Also, you don't want that in Cassandra, but that's neither here or there. Okay, so even if we now zoom in into what start is, right? So there's two problems here. One, there is a lot of implicit knowledge. You see there that there is an environmental variable called verbose that you kind of have to know that it exists, and then you have to set it up. And this, of course, is not true for all the services. So you kind of have to have a lot of implicit knowledge of the thing that you're doing. And the other thing is that there's a lot of boilerplate code, because the only thing that starts Cassandra is line 110. Everything else is either dealing with command line parsing or deciding what to log to the std out, and basically just doing a boilerplate. Now, if we even zoom to do start, like this is not standard at all. So it's really hard to answer questions like, what's the user that's running Cassandra? In which directory it's running? Like if you, let me take your attention to the last two lines. There's two start stop line. Why? Right? And there's a reason, of course, but because somebody put them. And one returns 1 and the other one returns 2 if it's failed. So it's weird, right? So yeah. And of course, if you actually want to answer a simple question, is my service running? There's no way that we can do it, right? I ask again, did I strike a nerve? Okay, cool. So yeah. So this is it. Now, this also has a lot of issues, because these are shell script. There's no dependency in them. So when you start a machine or when you stop a machine, these things has to run in sequence, right? Because there's no dependency between them. And you can put some sort of like ordering with numbers, but in general, like that doesn't make any sense. So start and shutdown was slow. Well, debugging shell scripts is hard, right? Because after 100 lines, like it's really hard to know what is actually doing something and what is actually just doing control flow. So in Unix in general, or Nix, we kind of figured out that to take things into the 21st century, this was not going to be good. And in Linux, a few new init systems appear. Upstart and systemd were kind of like the biggest one. They were an emerging technology. They went into a feud with each other, a healthy competition, and eventually systemd came on top, right? So then systemd won. And this is kind of like where we start with this talk, and it's the fact that either you love or hate systemd, it's kind of like to the side. Systemd is there, and it is on your machine. So let's see how we can take advantage of it.
All right, so I think it's pretty safe to say at this point that systemd is here to stay. It's in all of our major distributions. And the idea behind systemd is that you just tell it what commands you want to do, and you don't have to worry about a lot of the boilerplate that you had to deal with when you were writing init scripts. And systemd will attempt to choose the best way to run your service the way you tell it to. So here's an example of a systemd service unit. If you wanted to run the service as a certain user, you just have to set the user property to the desired user. If you wanted to change the working directory of your service, you just have to use the working directory property. And at this point, this is one of the few areas that look bash-ish. This is the actual command for your service. You just have to fill out the exec start property with the command that you want to run for your service. Notice how there's like pretty much no bash here at this point. Another cool feature about systemd is the ordering. So this is something you couldn't really do with init scripts. I mean, people kind of faked it by adding numbers in front of their scripts and things like that. But with systemd, you can tell it to run your service before or after other services, depending on how your dependencies look. And in the install section, you can tell systemd at what point during the boot you want to start your service. So in this case, we're using multi-user target. That will start it. This service, my app, as part of all of the user space services. So here's an example of how you could start myapp.service on the command line. You use system_start myapp.service, and systemd will do all of the setup required to set up your service, and then fork and exec it. If you want it to stop your service, just run system_stop myapp.service. Systemd will send commands to shut down your service, usually sigterm and then sigkill, and then clean up the state from your service. For consistency, we're going to run start again, and then if you were to run systemctl status, you get a pretty nice overview of what's happening to your service and whether it's started and whatnot. So in this case, we see that the service was running. This was a screenshot taken like 2 years, 3 years ago, so but you can see that it was running. At the point when we took this snapshot, it had started running 7 minutes ago, so systemd keeps track of all of this state for you. And you can also see below a brief overview of the process tree for your service. So these are all of the processes that have been started as part of myapp.service. And a lot of this is made easy due to C groups, a Linux kernel feature called C groups, which systemd makes pretty heavy use of.
Okay, cool. So this would not really be a systemd talk if we didn't talk about two things, C groups and socket activation. So let's get C group out of the way early in the talk. Okay, cool. So a C group is basically a control group, which is a way that the Linux kernel has to take processes and apply restrictions into it, right? So how much CPU, how much memory, how much network can it use? How much network? Well, you get what I mean. So it's how the kernel does that. And systemd definitely uses that part of the C group. But it also does a very clever thing with it. For every service that you start, like myapp.service, it creates a special C group for that service. So in this case, it will create system.slice/myapp.service. And then every service that runs, or every process that runs in that C group gets added to the C group. So you have main process, and then if main process decided to have children, they're also part of the process tree, but they're also part of the C group. Right? And if one of those children rebelled and decided to double fork itself and escape the parent, well, escape the parent, great, but it's also still part of the C group. So this is a nice way that systemd has to keep track of all the processes, right? Now, I don't know if you remember, like in the old days, again, we used to have an Apache web server, and that thing used to have CGIs. And CGIs were basically like shell script that get executed, right? And still shell script, they could do whatever they want. So a lot of the times, they just double fork itself. And then somebody says, like, restart Apache. You restart Apache, or you stop Apache, but all this side CGI process is still like hanging out, right? Now, with systemd, you have the main process, you still have the child, you still have that process root that is easy to track, but systemd can also keep track of all the processes. So when you say, systemd, can you stop my service? Systemd can actually like hunt down every single process that you have and then just kill the C group. And this is kind of crazy, because if you kind of think about this, before systemd, we had no reliable way of stopping a service with it. So that's something that, at least in my head, blew my mind.
All right, so now I'm going to talk about dependencies in systemd, because one of the goals of systemd was kind of to make your boot more performant by parallelizing a lot of the start of services. And so the way it does that is it provides properties to allow you to configure both the ordering of your services against other services and whether you require or depend on another service in order to start. And so by doing that, systemd kind of takes all of that information, creates kind of a tree internally, and uses that to parallelize a lot of the start and stops required in your unit. This makes the boot and shutdown process a bit more performant than having to synchronously run everything. So here's an example of ordering using the after and before properties. So on top we have app.service, and it wants to run after db.service. So you can specify that in two different ways. You can use after db.service, or in db.service you can put before app.service. And now when you run, if you try to start both of these services at the same time, they will be ordered in the way that you specify here, where app.service will come after db.service. If instead you want app.service to depend on app.service, so you can use the wants property. What this does is if you try and start app.service, it will also start db.service and also respect the ordering as well. However, wants is a weak dependency, so if for some reason db.service fails to start, app.service will just keep going. If you want something stricter, you can use the requires property here. That way, if you start app.service and db.service fails, then app.service will also fail to start. And of course, as you will eventually learn with systemd, there are multiple properties for specifying all the different granularities you want with ordering and dependency. You can read more about that in the systemd unit man page. All right, so now I'm going to talk about journald. So systemd journald is a pretty central part of systemd. It's the central logging system, and it aimed to solve a lot of the issues we had with syslog and traditional Unix logging systems. So syslog was relatively insecure. You could tell it you're whatever PID you want it to be, and syslog will believe it and log it to disk. There was no formatting with the data that is logged. Basically, everything was just a text file, and it was really easy for humans to read, but it was pretty inefficient to programmatically process because nothing was indexable. And with syslog, you need an extra service to manage. Whether the file system gets full, you need something to manage that. It doesn't really have rotation built into it, and rate limiting features were well limited. Systemd journald kind of is one daemon that attempts to fix a lot of these problems. Here's an example of a journald config. So you could still do things like tell it to forward the journal logs that are coming from your services to syslog. You can change the runtime max usage, where you want your logs stored. And of course, like I said, there's a whole multitude of properties that are not listed here. You can visit the man page to figure out how to configure the journal. So how do you get your logs into journal? Well, anything that's logged to standard out and standard error in your service, that ends up in the journal. So for example, if we have an exec start that echoes hello world, if we run journal cuddle, you'll see the hello world printed in the journal. You can also programmatically write to the journal. So systemd comes with a utility called systemd cat, and if you echo things to pipe things to systemd cat, that will get logged into the journal at the log priority that you specify. If you use something like pystemd, which is a Python library for systemd, you can modify the different fields and metadata in your log message before you log to the journal. And if you use a C library, systemd ships with SD-journal API and things like that. You can also modify the metadata that gets sent with your log. On the right, you can see a lot of the metadata that comes for free with each of your systemd units. So the ones that are underscored, systemd will just log those for every unit without you having to do anything. So in addition to your log line, you also get things like the UID, the host name, and then all kinds of things that are listed there. Okay, now I'm going to show you some examples of how we query the journal. So, like I said, well, I don't know if I mentioned this, but every field that comes with the journal log is indexable. So that includes things like the timestamp. So if you wanted to filter by logs since July 12th until July 13th, you can do that with journal cuddle --since and --until. If you wanted to change the output so that you see more than just your log line, you can use --output. In this case, I'm using verbose here. What verbose does is it gives you a listing of every field that comes along with your log line. If you want to filter by a certain process ID, you can do journal cuddle. In this case, I'm indexing by the PID field, _PID, and that will show me all of the logs from systemd. And of course, you can combine all of these fields together. So in this case, I'm looking up the logs from systemd lognd that were running as PID 1632 since July 12th, and that will show you that. The other cool thing about the journal is that it actually collects logs from your entire system, not just from systemd services. So if you wanted to look at the kernel logs, you can use journal cuddle --d message. -b is since boot, and that will tell you all of the kernel logs since boot.
Okay, cool. So now we are start digging deep inside systemd. So let's talk about a few features that systemd has. One of the most overlooked feature is template, and gets really overlooked because it's very simple, but it's very powerful, right? So people tend to just ignore it. So as we saw, if you want to create a service unit, you put a name .service. Now, if you put an @ symbol at the end of the name, and then you put these little placeholders, %y, what is going to happen is that when you call your app, after the @ you can put a word. And that word is anything. You define it however you want. It could be a configuration file, could be a path, it could be a user, any word. But whatever you put there, it's going to replace the placeholder. So if I put conf1 there, then you'll see that wherever I put the %y appears there. So that means that now, with a very simple unit, you can specify different web server, right? So this is a UWC server running conf1. But if I do conf2, it will run whatever definition of conf2 is. Another thing that is very common is that you put the @ the thing next to the @ is the user, right? So if you have a process like tmux or anything, and you wanted to make sure that this process run as a certain user, you put my app at Alivati or my app at Anita. And then each will run as a different process, but with just the same definition. So pretty powerful for what it is. And the promise socket activation. Okay, so this feature, to be fair, is not a systemd feature, but as many things, systemd have used this a lot. So let's see a little bit how a normal application would work. So you have your app. Your app, it's a web server, and it eventually is going to decide to bind to a port. So it has to open the port, it has to bind, it has to open the port, it has to bind, and then it has to listen, right? That's normal how it works. And then a request comes, and then you can serve it, right? So you see like there's a workflow. Your app, the port, the request. Now, what happens is that if your app for some reason decided to die, there's nothing listening to the port, so when there is a request, there is sadness. So, okay, so now socket activation. Socket activation kind of changed the paradigm a little bit, and it basically makes that instead of being your app, the one who starts listening to the port starts existing, and systemd will listen into this port. So you tell systemd, listen to port 80, and then a request will come. And then when that request comes, the first request, systemd will start the service, and instead of letting the service open the port, it will just handle an already open port descriptor, right? So now you give the response, and that's great. So the first advantage of this is that now the thing that opened the port and the thing that is using the port doesn't have to be the same service. So it can both run as different users, right? So systemd can run as root, and as you know, if you want to bind to port 80, you have to be privileged. So that means that your app has to be privileged at the moment that it's bind to the port. With this method, you will not need that. So your app can run as a very single user, and then the root user will start port. Now, if you take this and you mix it with the template that we just see, we can make some pretty cool blue-green or green-blue deployments. Basically, if you put the thing that is after the add, the version of your application. That version could be like a file on this, right, where you have a different binary, or it can be like a commit in GitHub. But whatever definition you can have systemd opening that port and forwarding traffic. And when you want to upgrade your application, you just say like, okay, so just start my application with a different parameter. So that will load the application. Now, if they're both binding to the same port, the kernel will do a round robin between these two, right? So then you can do some small A/B testing, assuming that you have the memory to do that. And then when you decided that version v2 is healthy enough to be the one that in production, you just say, bye, version 1, and then that's become the official one. Right? And now you have a very cool, simple deployment process with very little configuration, except like this management script that you have to do the rollout. Okay, cool. So how do actually you build these things? So if you want to start a service, you do a .service file. If you want to do a socket, you do a .socket. And there's many type of service file or unit files in systemd. This is called socket activation. There's one that I recommend reading that we're not going to touch here. That is called path activation, which does exactly what you think it does. When somebody accesses a path, some service gets started. It's pretty cool. But yeah, so this is my socket. And as you can see, it has the same section that the other. It has a unit and has an install. But you can see there's a socket section. And the socket section tells which port and which address it's going to bind to. And then you see that it also has this reuse port, which is the exact feature that allows you for two applications to start listening into the same port. Right? So this is the one that the kernel is going to use to round robin. So yeah. So how do you do this in code? Because like we still have to write the application to be able to understand this. So traditionally, when you start an application that is a web server, you will open a file, and that's that with statement there. Then you bind to an address and a port, and then you start listening. And then you accept your request, and then you start doing the process. This is your application, right? But this is the one in white is the logic for opening a port. Now, since you don't have to open the port, and systemd will already like give you a socket, you just say, instead of like opening, you say socket.fromFT. And then systemd comes with a really nice little variable that tells you where is that socket, and then you just specify the type of socket, and then your application just move on as it normally should. Okay, so programmatic access. Now, systemd has a nice, cool feature that it has a DBus interface, which is an IPC process. So anything can talk to systemd. So if you want to like get information out of systemd, you can do systemctl on batch, but also you can talk to systemd. And we at Facebook, we use systemd a lot, and we use Python a lot. So we create a binding for this, right? So we have a Python API to systemd, which basically what it does is that it exposes all the goodies of systemd into Python as like Pythonic APIs, right? And that's it. There's no magic behind it. So you will install it the same way that you will install any Python package, pip install systemd. I've been told that this thing is also in Debian, by extension Ubuntu. I've also been told that this is in Fedora and Apple. So we're good to go. And it works like this, right? So you open your service, and then you can do start, then you can do stop, as you would normally do. Now, it's the same thing that from status you can get it, right? So you can say unit.service.mainpid. Now, a nice thing here is that you get an integer back. So if you were doing like processing your shell script, this will be a text, and then you have to know the type, you have to parse it, and do all that magic. Since this is a real IPC, the thing that gets to you, it's actually typed. So since it's typed, you can actually get more complex stuff, like an array. So if you want to know what process are in my service, you can actually inspect this at runtime, right? And you get an array of tuples. What a beautiful thing. Okay, so basically you get all those things. Yeah.
Cool. So now I'm going to talk about a few more applications of systemd by talking about watchdogs and notifications. So if you set watchdog seconds in your service unit to a certain number of seconds, what it does is it tells systemd to expect pings from your service, in some certain number of time. If it ever exceeds the watchdog seconds, so let's say the service goes unhealthy, it no longer is able to ping systemd back, we time out, then in this case, systemd by default will just restart your service, and hopefully it gets healthy again and it can start pinging. And of course, this behavior is configurable. So here's an example of what this looks like from both the program side and also the systemd unit side. So on the left, we have watchdog second set to 3. So systemd will expect pings within 3 seconds from your process. And on the right, we enable the watchdog with pystemd using pystemd daemon watchdog enable. And you use pystemd daemon notify to send those watchdog pings. And so on the bottom, you see an example terminal of what that looks like, where the watchdog's enabled and it starts sending watchdog pings. If we decide to stop sending those pings, you see a notice from systemd that we time out from the watchdog and it will sig abort and kill the service. And beyond watchdogs, you can do this with notifications in general. So by default, systemd will send notifications when your service is activating, when it's reloading, whether it's started. But you can override these from within your service, within your program, by sending different notification signals. And so to do that in your unit, you should set type equals notify that tells systemd to expect your service to set up the statuses. And using pystemd daemon notify, you can set the status to loading, and then below in system_ctl status, you see that the service now says it's loading. And if you want to say that the app is now ready, you can do the same thing, send the ready signal, set the ready signal to 1, and update the status to app ready, and that will get reflected whenever someone runs system_ctl status. And of course, with systemd, there's like a whole host of different notifications you can send. This is just a few of them. All right, and now for the fun part, we're going to run some live demos using systemd and pystemd.
Where everything can go wrong, right? So, and I should have started this before, but okay, cool. I think I can do that. Is that a little bit better? Okay, cool, awesome. So as a fun thing, I named this demo systemd demo because system. Thank you. Okay. There you go. So that's one. Okay, so I need to set the stage so I can explain how the demos will work, right? So on your left, you have a Python shell. It's the regular as you have. It's just overloaded, but it's just on a Python regular thingy. And on the right, you're going to see some information that changed a little bit with every demo. In particular, I'm showing that this thing is running, this line over here. It is the demo, right? Okay, cool. So in Python, if you want to start a subprocess, you use the nice subprocess.run, right? So you do subprocess.run, bin sleep, and then I'm going to sleep for 300 seconds. And you can see that in the right, a new process has started, and it's a child of the process, and it's on the same TTY. Ergo is on the same C group. Ergo is on the same with the same user. Not Ergo, but it's also like a nice feature of this. So yeah. Now with pystemd, we have used a nice feature of systemd. Systemd has a command line tool which is called pystemd run. So since subprocess run, pystemd run, I mix them together. So now you have pystemd run. And what this will do, it will start, as you can see, bin.sleep, but it starts definitely as a different unit, right? So this is a good way for you to tell like systemd to start, right? Now, this is a proper unit that has a status. And you can see like it is running, it has that command, and it's actually so cool that systemd will actually create a service unit for this file. We're going to church. Right, so if I were to cut that file, you can see that it actually has like it's a proper service unit with a lot of information there, right? There you go. So now let's take this a step further, and this is actually cool. So what I'm doing here, I'm starting a service unit. So as you can see, it starts somewhere else. But I'm binding the std in of my Python REPL and the std out to this std in and std out of the unit, of course, inverse. And then I'm just binding those things. So even though I am in a Python REPL, I actually can interact as if I were if I were that unit, right? The other thing that is cool is that since I named this my service, and I'm going to name all of these things my service, you can see that I can actually see the status of this, and I can see the unit that gets formed. So this is going to kind of like help us inform. And with this, I hope everything was clear. If it wasn't, you're going to catch up. Don't worry. Okay, so let's start with the first example.
All right, so in the first demo, we're demonstrating two sandboxing features that systemd provides, protect home and protect system. So setting protect home to true will make it so that within the view of your systemd unit, the /home directory will be completely empty and inaccessible. This is compared to on the right, where outside of the systemd unit, on the host, you actually have home directories. And with protect system strict, it makes the entire root file system view from within your systemd unit read-only. So if we try to touch something within the systemd unit, you see that we get an error about read-only file system, whereas on the right, outside of the systemd unit on the host, we're able to touch things.
Okay, cool. So the next example is a little bit more granular, right? So that was like a blah thing. And the logic of that is that if you start your web server, you don't want your web server to have access to the AWS key of every user of your machine, so you must better unmount it. Now, if you actually want like granularity here, you can set up like read-only directories, and then this directory in particular, now it's mounted, but it is read-only. Right? I'm not going to try everything. You have to believe that the thing that is named as read-only is actually read-only. But yeah, so that's the one. Now, inaccessible directory shows the other thing that you saw, right? Which was that the home, even though it exists in the real system, for this service, it doesn't exist, right? And read-write directory is what it is. Bin path and bin read-only path is also a very interesting feature, because now we can take this directory over here, and what we're saying is that attach whatever this thing was as another path. So inside the service, you can actually like toy around with the actual file system, and then you can see that this is mounted as something else, right? And this is true not only for that, but for binaries, right? So in this case, Python or files, not binaries, or regular files. So Python exists there as a directory that was just mounted as a different thing, right? So this is interesting, and go. By the way, Simon did a talk about chroot and proot about this that covers similar things, but he does it like from scratch without the help systemd. So once the things are online, I really recommend seeing that.
Okay, so more sandboxing features. With private temp, you can create like a tempfs that is unique to within your systemd unit. This is completely different from temp outside of the unit. You can also create a temporary file system with the temporary file system property, and in this case, we have one under var cache mys. You can also create a private network inside of your systemd unit. So this will create a new network namespace so that it can't access the network outside of the loopback interface. And you can also use private devices true, which means that /dev will be a completely new mount, different from what's on the host that you see on the right, which is outside of the systemd unit.
Cool. So this feature is also kind of cool, but it takes a little bit of a turn, right? So these come from the fact or the general knowledge that you should start every service with a different user. So if you start a web server like an Nginx, you start as a www user. If you start a Postgres server, you start like a PSQL user. But are you really going to do that with every single service, like this really crazy script that you have that just deletes partially downloaded files? Well, the answer is yes. And to do that, you do it with dynamic user. So dynamic user will, when your unit start, will create a user on the fly, will add into the file system, it will add it to the system as much as it can, and then this is the user that it has. That you see the number 64885, and if I do who am I, you see that actually the file doesn't exist because this is not updated in the etc password. This is updated on an NSS switch. So yeah. Now, if you remember that PYD, it says 64885. Now that's PYD for the same service, or name service, can get reused but this is true only for the same boot, right? So this is a good way kind of to preserve the logic of maintaining between one and the other.
Okay, so if you wanted to do things like filter IP addresses, of course systemd has something for that too. You can use IP address deny, and if you pass it all zeros, that will tell it to deny all IP addresses. So when Alvaro tries to ping one of Google's DNS servers from within the service unit, he is unable to. However, we did allow 8.8.8.8 using IP address allow, and you are able to successfully ping it from within the systemd unit.
Okay, cool. And now we're seeing C groups in faction. I don't know if you noticed, but this bash actually took a little bit longer to start. This is because we are actually using, we're actually setting up the maximum CPU that this service can use, right? So here we say that we can use only 20% of the CPU. So if I remember how to use this, is that how we use it? Sorry. Yeah. Yeah. Okay, so I can use stress and G and do CPU. Oh, wait. Why are you failing to me now? Stress CPU. It's 0? Okay. No, it's 1. Okay, never mind. Okay, so this is actually using 3 CPUs. Live demos. We are going to fix this, don't worry. Yes, we're here. We're back again. Okay, go. So it was stress ng CPU 1. Thank you, Simon. Okay, so what you can see, like we start stress ng, and this process can only use 20% of the CPU, and that's the thing that we're actually trying to aim for. If I use CPU 2, you're going to see that between these two, they cannot actually use more than 20%, right? So they kind of like are doing the same thing. Now, taskmax is actually like pretty cool because this actually controls the number of times that you can fork exec into the unit, right? So as you can see, I'm starting batch. So the task is 1, as you can see it right there. My mouse does, yes, it works as a pointer. Okay, so if I start as sh, start, and now that number goes to 2. If I do sh, goes to 3. 3 plus 1 equals 4. You see where this is going. And now when I do one more, it basically stops the forking, right? So if you have a service and you know that it cannot really like avoid fork runs and stuff like that, this is a good feature. Keep in mind that this is a feature of the kernel that systemd is exposing to you, not a feature of systemd. And finally, well, I need to exit actually all the things that I have. Okay, perfect. Now I can do Python. Python uses a little bit of memory. That's one of the complaints that people have. But yeah, so if I do x equals, and I decide to create like a long string, like hello, yeah, hello, and then do a very long number that I've been told this is long enough. Yeah. You're going to see that systemd is going to kill the process. Now you see that I'm still on batch, right? So what systemd, actually what the kernel is doing is the right thing. It is like there was a process, it went, the whole unit went over the memory, the killer start, and then slaying the minimum amount of process that would free the most amount of memory. And of course, if you want to know what umd, check out systemd. Okay, now, since we failed, we actually need to do a couple of things like go.
All right, so we're going to close off with the last demo, which really demonstrates how systemd units can toe the line between like containerization. In this case, we have a Debian root file system. If we set that to root directory, we will have our systemd unit appear as though it is now running Debian, when actually on the host outside of the unit, we're running Fedora. So inside the unit, you can do things like apt install SL, and you can actually run it as usual as any regular Debian application.
And you cannot exit that because that's the reason why the application exists. So we exit, and then we are done. So, questions? Go ahead, sir.
You mentioned that within the scope of this socket activation, so systemd will listen on a particular port, and then the request comes in. And the question is, what will happen then if the actual application will take, let's say, 5 seconds to spin up? Will the systemd hold that connection, or?
No, so yeah, so there's features for timeout and stuff like that. That's also particular in the same unit. You can do like timeout when the unit has to start. But you're right. You will pay the price, or the person or the request that will pay the price for starting up the service is the first one. That is definitely true what happened. But yeah, but there's features that you can do for timeout. So you can say like systemd will just call to the connection and just put it into the listening queue for new connections. That also happens, right? And then when the unit's starting, you can say like timeout on the unit. And then if the unit timeout does start, you can restart again or can just die, and then the connection gets closed.
If the service goes down, the systemd restart automatically?
So that's not by default, but there is an option. There's an option called restart, and then you can say on failure, or on everything, or on nothing.
So I think the socket activation topic is pretty cool. So for socket activation, does the application itself have to be compatible with it? I mean, you showed some code changes, right?
Yeah.
So the application has to already have the logic to support it.
Yeah. So the good news is that a lot of random application out there does work with this. Like a good example is Nginx, because the way that this works is that systemd will set, I'm not sure if it sets an environmental variable or there is no, I think it sets an environmental variable running, and a lot of applications just check if that environmental variable is there, and then you can set in your config actually like started from systemd. I'm pretty sure this support. I think Postgres also support, MySQL probably, Cassandra doesn't, but that's Cassandra's fault. Cool, go ahead.
So can you talk a little bit about some of the ancillary services that systemd has provides or has become part of systemd over and above the process management stuff? Again, my favorite hobby horse here is DNS, but anything else?
Yeah, I can talk about a few of the daemons that come ship with systemd. So for login, we have systemd login-d. Of course, we already talked about systemd journal-d. More recently, we upstreamed and pushed out systemd oomd, which is a user space killer.
oomd?
Oh, I did talk about oomd.
Oh, yeah, sorry, I didn't. Yeah.
There's systemd nspawn if you want to use containers and stuff. Systemd machined can manage things like your images, virtual machines. Man, I mean, those are like the ones I use most frequently. Oh yeah, systemd networkd. If you don't want to use network manager, you can use systemd networkd to manage your network interfaces.
I think next release is going to come with an Office suite. So you have systemd Excel.
We've joked about systemd text edit, but I don't think that will become realized.
Well, you can do systemctl cat, and that kind of displays. I think there's a systemctl
Yeah,
edit.
systemd cat, systemd analyze to help verify and analyze systemd units.
Yeah.
Systemd boot, if you want to replace your bootloader with something as part of the systemd project. Am I missing any? I think. Oh yeah, systemd timedated.
Yes. But all it does is like manage a file, if I'm not mistaken.
No, just like NDB.
Oh really?
Like basic NDB syncing.
Okay, cool.
No,
I'm not the
I
first one.
omitted systemd resolve D since you brought it up, and it's not everyone's favorite, so.
What? The sir in the back.
How do you feel about using systemd to replace some of the cron jobs?
System
Systemd timers.
System timers, this is very good. We didn't touch it, we should have touched it. Let's give our answer yes or no at the count of 3, if we like it or not. 1, 2, 3, yes. Yeah, in general, I like timers. They're more, I would say like the barrier of entry to learn how they work with cron, like against cron, it's higher because cron is something that we have seen since we were babies, right? But it's way more flexible, right? Yeah.
When you're shutting down the Linux system, will systemd shut down services in the right order? And if some service is taking a long time to shut down, will it wait for it to gracefully shut down?
So the timeout for every service unit is configurable. By default, it should be 90 seconds. But at some point, your system will have to shut down. The service will time out. It does its best to gracefully shut things down with sigterm, but exceeding the timeout, it'll just go ahead and SCaLE everything.
That's something that we didn't talk, but as you can see on the init script for Cassandra, somebody defined how to stop Cassandra. Well, we have never defined a stop. And you can do that, but the point is that we kind of know how to stop a service, so let's just do the default.
Especially for database, you need to be gracefully shutting down, otherwise,
Yeah. Well, yes. You decide what signal to send. You decide what to wait and what to do once the signal it's not happening, right? So you say sigterm, for instance. When it finishes, you can actually send another sigterm, and then eventually systemd will take the responsibility out of your hand and say it's more important to shut down this machine than to preserve your cat pictures.
Are there any visualization tools that would help? One thing that systemd does very nicely is order and provide dependencies for startup, and that's one of its key selling points. Is there any visualization tools that allow you to sort of look at the systemd configuration and see what's going to happen, as opposed to just chasing all the tails, so to speak?
There is visualize, right?
There's like the boot charts.
Yes, there are bootstrap and trust, but yeah. And there is, I think there's visualizer, but I definitely don't know.
Yeah, and in systemd analyze, you can actually plot the boot process. It's not supported yet for shutdown, and I don't think it does it for like arbitrary start of units either. But if you want to plot like your boot, figure out which services were taking up the most time, things like that, that is in systemd analyze.
So is that the last boot that just happened, or it's you make changes and then you see, well, what'll happen next time? That's kind of what I was going through.
Oh, it only does the last boot. It doesn't like simulate the next
but
boot.
systemd has a systemd dependencies, and all you have to do is put it into the first target, a systemd start, which I can't remember the name. But you will probably do that, and then it will show you what is the order or what it's going to do. But you can do this for like anything, right? Like literally any service, so every unit, you can, I can't remember, but I think there's dependency thing. And it shows you like the dependencies of the thing that you're going to start. And if you do it with a target, you see what's going to get started with the target.
like systemd Grafana.
Splunk, yeah. We're writing it in Rust. I hear yes somewhere.
You jest, but we are considering writing systemd daemons in Rust in the future.
Something that you don't know, Anita is a core contributor of systemd. Okay, seems this is good. Thank you very much, people, for coming. Really appreciate it. We did good time.